There you go. Okay, so if anyone needs to do anything up here, this mute is for the room.
Yeah.
And this mute is for the computer.
Oh. So that
YouTube.
That lower one would be YouTube.
It would be
as well?
YouTube. Yeah.
Okay. Yeah, we can click that now. I don't really want to. I think.
Oh,
That one? Yeah.
no, that's muted now, isn't it? So I'm gonna go to.
Oh, click that off again because that's.
Good morning, ladies and gentlemen. Welcome to our design project presentations this morning. We're about to get started here in a minute. We had a couple things to get set up before we begin. So the format's going to be, we'll have students present. I'll introduce each of our students at the end of their presentations. We'll take questions from the audience. We're working on getting, be able to take questions from the live feed. Hopefully that works out for us. Each presentation is going to run us about 20 minutes, half hour, before we move on to the next. So I'm just going to get started right away. We'll jump right in. Up first, we have Cale Trim. He's going to be doing his project presentation this morning's on his oceanographic research vessel. I'll let him introduce the particulars, and let's begin. Thank you.
Morning, everybody. My name is Cale Trim, as previously said. So yeah, third year NARC student, and this is my 84-meter oceanographic research vessel. So jumping right in, this research vessel is designed for ocean exploration and scientific missions. It is non-seismic oceanographic research. It is being primarily operated in the South Pacific, with the operations being conducted by NOAA, which is the National Oceanic and Atmospheric Administration, based out of the U.S. It will be flagged in the US and is designed with Lloyd's Registry in mind. The capabilities of this vessel are the biological and chemical research, chemical, physical, and geological oceanography, as well as the towing of oceanographic instrumentation. Overall, the mission of a non-seismic oceanographic research vessel is to enhance our understanding of the oceans, as well as bring a comprehensive data collection to light and make sure that the oceans are sustained for generations to come. The reason I chose this vessel for my design project is because I come from a yachting background, and the aesthetics of the research vessels are something that I thought would be fun to play with, as well as the background information that you get to do to make sure that the vessel has a good flow to it when working on board. So moving on. The first item that we did in our design spiral was creating a state-of-the-art analysis. For all of our projects, we were given main design parameters that would be the starting point. And for mine, that was a range of 10,000 nautical miles and an endurance of 60 days. The evolution of the design of research vessels over the years has made the task of collecting this data a little bit more difficult, as the trends have changed from a little bit more of a centralized accommodation block and more lab spaces with lower aft decks to a large aft deck, mainly forward accommodation block organization of the vessel. As well, the design parameters for this one, because of the endurance of it, the fuel capacity was of great concern early on, making sure that we could obtain both of those design drivers. The final parameters that were stated for this vessel through the SOTA were a range of 10,000 nautical miles, the endurance of 60 days as previously stated, a dead weight of 1,500 tons, a displacement of just under 4,200 tons. The length was 84 meters, a beam of 16.8 meters, draft of 5.5, max speed of just under 14 knots, and a block coefficient of 0.53. And then this vessel in particular that I designed can house 50 souls on board, with 26 scientists and 24 crew being split. So as the design went on, we began with our lines plan development. This was selected for my vessel, or these lines were selected and designed for my vessel because of the efficiency performances, as well as the ample usable aft deck space. So for this vessel, it has a vertical bow, which enhances the ride experience for the scientists and crew on board, as well as making it a little bit smoother when towing. The design also has a flat transom, as you can see, in the aft area here. And this is done so that then we could have twin azipod thrusters in the rear there. So a flat mounting spot was crucial. The last thing to note is, while we were doing this design, we did it in MaxSurf stability. Actually, no, not MaxSurf stability, MaxSurf period, because the stability one is for different things. But as we designed, we made sure that the displacement and the block coefficient were being monitored, so then the final vessel parameters were met. The GA was started very early in this semester, or not this semester, but this year, and was developed throughout all 3 semesters of the program. So diving right in, the aft deck is the most used spot on the vessel for research to be gathered. This aft deck has a 35-ton A-frame, as well as 2 5-ton knuckle boom cranes on either side for handling over the sides in the aft area. It also has winches on the deck here, which can either have solid lines or be optic cables for handling any ROVs or hydrophones, that kind of thing, over the aft end. Moving forward, the main deck, or the deck 01 here, has all of our specific labs to the vessel. So this includes the biological, chemical, climate controlled, as well as the CTD lab, which also has a telescopic boom crane off of the side for deployment of the CTD equipment. And moving forward again. So right below this deck is where the winch room is located. This is where some of those cables will be fed up through the deck and off the aft end, so that then the research can be collected. The general labs are also in this aft area, which have quick access to the upper deck through stairwells on either side, on these sides here. And they come in a clean, dry, clean, wet, and a wet, dirty lab for all aspects that might need to be done on this vessel. Continuing forward, the main area of the vessel where the dining experience is, as well as the lounge for the crew and scientists, is located on this deck for easy access to both accommodation areas as well, which are below and above this. I'm going to skip forward one for right here. So right below that area, the stairwell in the center goes all the way through the vessel to connect the whole thing. And this is where the crew accommodations are. I grouped them all together so that then the vessel would have a good flow to it, with the crew and the scientists being grouped in specific areas. Going back, the engine control room and server room, battery room, and workshop are all accessed off of that rear area there, with access to the engine room being just forward of that. So going up to the second superstructure deck, the main scientist crew quarters are here, as well as the captain's cabin and the electronic computer lab. We also have access to the aft deck here, where there could be spots for either 2 containers or 2 mobile lab units to be craned on at the start of the mission to satisfy different parameters and different mission capabilities of this vessel. And finally, the bridge deck, of course, where the ship is steered from, as well as where the operations of the aft deck are monitored at these 2 aft stations overlooking. So yeah, moving on, we can get into the powering and propulsion aspect of it. So for this vessel, we started by getting the effective power estimate. This was done with methods such as Hultrop and Menin and the Keller's formula. This gave us a total resistance of just under 500 kilonewtons, at the 13.6 knot design speed, with an effective power of 3,400 kilowatts. The propeller size and selection was done using KJ charts, propeller design category 4 specific, and the Furuno method. And this gave us a 3-meter V575 propeller. And then finally, the brake power, of course, which is what the vessel will be implementing on, getting a little stumbled here. That's what the vessel will be installed with its gensets to power the azipods out the rear. So for these, we have 3 main gensets and 1 hotel genset. The breakdown is as you see here. We have 2 main gensets, which are all MAN BMW at 2,500 kilowatts. The third genset is a 1850 kilowatt genset, and the hotel genset came out to be about 810 kilowatts after we did a few analyses. Moving on to the structural design, which was a big portion of the design spiral. It took quite a lot of our time. The structure for this vessel was done with Lloyd's registry in mind, and everything was checked against it. It was transversely framed, and it is of steel construction. The reason for the transverse framing is because the design of this ship has a lot of shape to it. Oops. Sorry. So because of this and very little parallel middle body, it made a lot more sense for it to be transversely framed. A problem area arose when we were looking at the engine room in specific. Because of the design envelope of the engines, the two deck space had to be broken out and cut a hole in it, as you can see here. This was for the design envelope of the engine for maintenance. So to solve this problem, we installed pillars and beefed up the girders in this upper area here. So this way we could have the design envelope met and be able to access all aspects of our main gen sets. Moving on now, the capacities. So on this ship, because of its endurance and range, the fuel capacity was quite large at just over 1,200 tons. Because of this, you can see that the majority of my red tanks there are fuel. And this also had to be isolated from the side of the hull due to the Lloyd's registry rules, and also Transport Canada and MARPOL. So with these in mind, we have a double bottom in this ship, as well as wing tanks for ballast that separate the fuel from our steel hull, for if there was ever an accident, it wouldn't be spilling out into the ocean, causing quite a lot of damage. The other capacities on board this vessel are the freshwater capacity, which it will hold 123 tons, which is a week's worth of water for the vessel. It will also be equipped with a water maker on board to replenish this during the whole trip. The black water capacity is 47 tons. The gray water capacity is 47 tons. The dirty and clean lube tanks are both 1.4 tons. Hydraulic fluid, as you saw, there is lots of equipment on board this vessel that uses that. So there's a designated 2.8 ton hydraulic fluid tank, and then ballast is throughout the whole ship to level it out in different trimming conditions, as well as to keep the fuel off the hull shell. And this came out to be 940 tons. So this last semester, we did the trim and stability portion of the design. So once the capacities are finished and the hull is designed and you have a lot of your exterior or external loads figured out, you could run the conditions using the standards from IMO and Transport Canada. And with these conditions, I ran 4 different conditions. I ran the light ship, the port departure, the mid voyage, and the port arrival condition. As you can see on the top one there, that is my light ship condition, and the vessel naturally sits at a draft of 3.4 meters with a 1 degree trim to the stern. The port arrival is the lower image here, and this vessel the port departure, and this vessel sits at the 5.5 meter draft. So with all of the tanks loaded, and a little bit of ballast on the port side, just to level out some of the cargo we're carrying, we could get that 5.5 meter draft and just a little bit of trim to the stern. The final point of our design spiral that we went through was the cost estimate for the vessel. For this vessel, the cost was consisting of direct and indirect costs. The breakdown, which we created through the direct imperial methods, were a steelwork labor cost of $3 million, outfitting labor 4.4, machinery plant material costs at 9.1 being a great chunk of this, and the estimated vessel price being $47 million, including the percentage of the shipyard's time as well. So yeah, that is the design of this 84-meter research vessel. If there's any questions, I'm happy to answer now. Yes, you in the back. For these guys? So the cost estimates, so we did them based off of the, it was the, what's it called? I forgot to write that down, but it was the empirical methods that have been developed for years leading up to this, and then they were adjusted based off of the average labor rates in each division. So we looked at the average labor rates for steel, which would be the welding costs, as well as the installation. Sorry, is that on the right avenue? Domestic or international? So this is all U.S. pricing. So we went off all of the U.S. Cost adjustments as well. Yeah, in the front. Do we have that microphone floating around? It's kind of hard to hear. Do you have any? It's up there. Okay.
Question regarding your propulsion selected as a box.
Yes.
What's the reasoning behind as a box as opposed to a conventional?
Yeah. So the reason for the azipods, was actually because the vessel has different operating modes. I probably should have touched on that, but the main one for going with a diesel electric arrangement over a mechanical arrangement is because when you're underway towing some of this material, there's a need for a quiet drift mode. So that'll be primarily run off batteries with just a little bit of assist of the bow thruster and the azipods to keep course corrected while it's going in the currents.
Right. Electric motors, not power shots. Supposed to as a box, or why as a box? Have any station keeping ones?
There's not much well, there is a little bit of station keeping, of course, when we're running and dropping any of the ROVs over the side or anything. So this is equipped with DP1. And I guess that was my main reason for choosing a azipod over a mechanically, yeah. Is that cool? Yeah.
What design aspect do you take into consideration?
For engine flooding? Is that what you said? Sorry, I'm not sure if I understand. Maybe you could just speak up a little bit more.
What design aspects
What design aspects? Right. So we didn't touch too much on that. Obviously, being that the vessel has a double bottom for keeping all of that separate, so then we must apply the balancing system and wheel system and start pumping that out. Because this is not a passenger vessel, we didn't have on a two-part standard or anything like that. So it is equipped with all of the necessary building pumps and all of that to get into that water. So because we didn't do electrical analysis regarding average bank in our courses, I was able to develop on that. that would then be something if I had more time and a little bit more resources to go through it, I could figure that out, really all of its capabilities with that. Cool. Thank you very much for listening. Thanks. That was for the next person.
Good.
Okay. We're gonna plug in. Oh, okay, I don't know what. So use this one? Okay. There's already one in here, so is this the one for this clicker? Or is this the one for this clicker?
I think this has got to be plugged in here first.
There's already a,
No, that's USB up here. So. HDMI.
oh, yeah. Don't you log into my account? Is it already logged in? Mine's HDMI's on the back of mine. Is it on the back of this one?
Yeah. What is
Oh.
yours? Oh,
How do I use that one?
plug into the main one.
Okay. How do I do that?
You don't need to.
Where do I plug in? Okay.
It's right here. PC. Then you should be able to log in.
I thought that was the PC.
Oh my, this is live. How do I get around this?
Yeah, I don't know if this goes straight up.
Like, this won't come out. That's everything.
It should be fine. It should be on right after drive.
What?
It should be on right after drive.
Is it on?
It's plugged in. This is the other one.
It's all screwed up.
It's all screwed up.
Yeah. My home fix is shit. I'll take that.
I don't know what the rest was. Relax.
So next up on presentations is Bethany Michelin, and she's got a
200 meter impact.
200 meter Ropax ferry, and Bethany's part of our third year marine systems program. So go ahead, Bethany.
Good morning. Thank you all for coming. My name is Bethany Michelin. I'm a third year systems student, like John said. I picked a 200 meter Ropax vessel modeled after the one that supports Nova Scotia and Newfoundland. And today my presentation is on the safe return to port regulations and how they affect the Ro-Ro ship design. So first, a little bit of history on the Ro-Ro ships themselves. They first started in the 1850s to carry large trains across rivers when they couldn't fit on the bridges. Its first land-based application was in World War II, and they were used for tank landing crafts, bringing them back and forth during the war. And in the 1940s, merchants started using them for carrying cargo, decreasing their loading times because the cargo could just drive on and drive right back off. And then the first drive-on berths were handled in 1953, so it was the first time passengers and people could drive their own cars on. And that year, over 100,000 cars were handled. So with the new publicity with people going on the ships themselves, the publicity around the accidents involving the Ro-Ro ships made it seem like they were a lot more dangerous than every other ship out there. And the World Casualty Statistic for 1994, published by Lloyd's, shows that the loss rate per 1,000 ships was 2.3, which is the average figure for all ships. However, when we look at other statistics, we kind of see a different picture. When looking at lives lost at sea between the years 1989 and 1994, 33% of all lives lost, which is 1,544 people, were lost in Ro-Ro ferry accidents. All other types of ships only make up 63% at 3,000 lives. These are 4 big incidents on Ro-Ro ships. Princess Victoria in 1953, the Herculeon in 1966, the Hero in 1977, and the Estonia in 1994. So starting with the Princess Victoria, she was the first ever Ro-Ro ship to go down at sea. Huge waves due to weather that night damaged the lower stern doors. She was equipped with guillotine doors to protect the stern doors from the wave conditions. They weren't often used because it was deemed that they took too long to lower and raise. However, this night particularly, they couldn't be lowered even if they wanted to because they had already been damaged due to weather. So that night, 133 lives were lost. Next is the Herculeon from Greece in 1966. The night she went down, the company that owned them, this company, was actually advertising that their ships were the safest out there, specifically mentioning the Herculeon. The weather that night was so bad that smaller ships were prohibited to set sail, but they believed that due to the size of the ship, she could handle the weather conditions. Also, that night, she was delayed 2 hours waiting for a refrigeration truck to board. That truck ended up being either loosely secured or unsecured. It's not entirely sure. And during the weather, she shifted and slammed into the midship doors until they gave way. She sank and 264 lives were lost. Next is the Hero. A year before she sank in 1977, she had a very similar close call accident. Water flooded the lower trailer decks due to heavy weather. However, this night, the change in weather allowed the water to flowed into the engine room and pumped out there. The night she sank in 1977, heavy damage was done to the forecastle decks and the stern doors. They attempted the same technique, pumping it out through the engine room. However, it was unsuccessful and she sank, though only 1 life was lost that night. And then there's the Estonia. So she went down in 1994, and the visor that protected the stern doors was separated and the loading ramp was torn off. The vehicle decks were flooded, and a list of 15 degrees at start and ended up at a list of 90 degrees. She lost all 4 of her engines, and at least 852 lives were lost. In 1983, an important study was done by DMV and was submitted to IMO, and this is what they found. Between the years of 1965 and 1982, there were 341 ship casualties. 217 were designated as serious, and 36 resulted in total loss of ship. They looked at some of the reasoning behind these incidents, and this is what they found. When it comes to causes of serious casualties, 24% was caused by ship collision, 17% was caused by machinery damage, 17% was caused by grounding, 16% was caused of shift of cargo and operational faults, 14% was caused by fire and explosion, and 12% was deemed as other. When it comes to total loss of ships, it was shown that 43% was caused by shift of cargo and operational faults, 25% due to collision, 18% due to fire and explosion, and then 14% deemed as other. So when looking at this, more than 70% of all Ro-Ro total losses due to collision resulted in loss of lives, and 60% reported collisions would have capsized and sunk in less than 10 minutes. So from this, they determined these problem areas: the lack of internal bulkheads, the cargo access doors, the stability, the low freeboard, cargo and storage, and securing, life-saving appliances, and the crew. So a little bit on each of the problem areas. First is the lack of internal bulkheads. So on a conventional ship, the hull is divided into numerous separate holds via transverse bulkheads, which can delay or limit flooding and fire. Though with the ro-ro vessels, the through decks, such as the car decks, make it possible for water to enter and flood rapidly, which also introduces large amounts of free surface effects. The cargo access doors at the bow and stern are possible weak points. They can become damaged or warped over time, especially if they're also being used as the ramps for vehicles. The next is stability. So the movement of cargo on vehicle decks can affect the stability, meaning a sudden inrush of water from hull damage or watertight failure can be more serious and more rapid. Rower vessels also generally have larger superstructure when it compared to other vessels, meaning they can be more affected by bad weather and wind. And there's low freeboard. Cargo access doors on cargo-only ro-ros are very often very close to the waterline, meaning a sudden list caused by something like cargo shifting can bring the threshold under the waterline and may result in a sudden rush of water, in turn creating more list. There's cargo storage and securing. A list can cause cargo to break loose if not correctly stored and secured, which can be made worse by cargoes inside of trailers and containers, which cannot be seen, and heavy loads breaking loose can cause other loads to break loose, as well as causing list, spillage, and worst case scenario, hull damage. Life-saving appliances can also be a problem area because the placement of the lifeboats can be affected if a ship lists so badly that it's either hard to drop the lifeboat on one side or impossible altogether. And finally, crew. So human error is a possibility in any case, but when it comes to ships with special requirements and all these problem areas listed, it's especially vulnerable to human error. From these identified problems, the following regulations were created. So first off is Regulation 8 and 8-1, special requirements concerning passenger ship stability and system capabilities after flooding casualties on passenger ships. So the first regulation, the special requirements concerning passenger ship stability, it aims to enhance stability and safety on passenger ships, both intact and damaged conditions, ensuring that they meet stringent stability criteria to protect passengers and crew in various operational and emergency situations. The key points of this regulation are the intact stability, the damaged stability, the subdivision and compartmentalization, survivability requirements, loading conditions, emergency situations, compliance and verifications, and maintenance and training. The Regulation 8-1, system capabilities after flooding casualty on passenger ships, aims to ensure passenger ships can maintain essential systems and functionality after experiencing flooding in one or more watertight compartments. Key points being the essential systems, which I'll touch on in a minute, redundancy and separation, damage control, operational capability, which in terms of this regulation is operation of essential systems for a minimum of 3 hours after water flooding casualty, allowing sufficient time to either return to port or safe evacuation if necessary. Crew and training drills, maintenance and testing, and compliance verification. So what are these essential systems? When the regulations talk about the essential systems, though they are not limited to this list, this is generally what they're referring to. The propulsion systems, the steering systems, the electrical power generation and distribution systems, fire detection and extinguishing system, bilge and ballast systems, navigation and communication equipment, flooding detection and emergency lighting, and internal communications. These systems must have redundancy and be separated so that if this often involves duplicate systems in different compartments with the use of watertight bulkheads. Next is Regulation 21 and 21-1, the periodical operation and inspection of watertight doors in passenger ships, and the flooding detection systems for passenger ships carrying 36 or more persons. So for periodical operation and inspection of watertight doors in passenger ships, it aims to ensure continuous operational readiness and reliability of watertight doors, side scuttles, valves, and other closing mechanisms that are crucial to maintaining watertight integrity of passenger ships. And this regulation sets out the requirements for regular operation, inspection, and maintenance of these critical components. Its key points being regular operation and inspection, frequency, testing of watertight doors, record keeping, maintenance, training, operational readiness, and inspection by authority. Regulation 21-1 is the flooding detection systems for passenger ships carrying 36 or more persons. It aims to enhance the safety of passengers ships carrying 36 or more persons by requiring installation and maintenance of flooding detection systems. Key points being the flooding detection systems, coverage of detection, system requirements, alarms and indicators, testing and maintenance, documentation, and crew training. So, the detection system requirements. The flooding detection systems must be capable of detecting flooding in all watertight compartments that are not accessible during normal operations, compartments below the bulkhead deck, and spaces that extend above the bulkhead deck and are used for cargo and machinery. All systems must be designed to prevent false alarms and redundancy features to continue operation if a single point failure situation happens. And there's Regulation 22, prevention and control of water egress. This aims to ensure the structural integrity and operational safety of passenger ships by preventing and controlling water egress. The regulation outlines the measures required to maintain watertight integrity and manage water egress to protect ship stability and buoyancy. Its key points being the watertight integrity, its closing appliances, operation of watertight doors, openings in the ship's side below the bulkhead deck, pumping and drainage systems. And when talking about the pumping and drainage systems, it is talking about all pumping systems, referring to bilge systems, ballast systems, and any piping systems capable of removing or handling water from any compartment. The structural protection, the periodic inspection and maintenance, training drills, documentation and records, and regulatory compliances. And the last regulation is Regulation 23, special requirements for ro-ro passenger ships. This addresses the specific safety concerns for ro-ro ships and RoPax vessels due to their unique design and operational characteristics. The regulation aims to enhance the safety of these vessels by stipulating additional measures to manage flooding, fire hazards, evacuation processes. Its key points being stability and damage conditions. So a passenger ship must meet stringent stability requirements in the event of damage and must stay afloat when one or more watertight compartments are flooded. Watertight doors and bow and stern doors. Bow and stern doors must be fitted with effective locking arrangements and have indicators to the bridge that show the status of all doors. Drainage systems. Effective drainage systems must be in place to manage water on all vehicle decks. This includes scuppers, freeing ports, and pumps capable of removing water quickly to prevent stability issues. Fire safety measures. Enhanced fire detection and suppression systems must be installed on all vehicle decks and other decks at high risk of fire. Escape routes and evacuations, surveys and inspections, documentation, and additional safety features. So these are known as the Safe Return to Port regulations. So how does this affect ship design? So the practical application of these regulations can be boiled down to about 3 points: multiple engine rooms, redundancy, and system segregation. So multiple engine rooms are used to ensure redundancy in the propulsion and power so that loss of one engine room does not mean total loss of systems and total incapacitation of ships. Redundancy has to do with systems and electrical power being redundant, so in the case of loss of an engine room or compartment, the ship can still operate if one system fails. And then system segregation, it is essential systems, as listed before, must be segregated in a way so that damage to one part of the ship does not incapacitate the entire ship and an entire system. So now talking about my project vessel. So at the very end of first year in MESD, we do a similar ship project and decide what kind of vessel we want to do. I decided I wanted to do a ferry. So at the very beginning of second year, we were given previous Naval Architect students' drawings, including the GA and lines plan, and this is what we based all of our systems designs on for the next 2 years, ending in this. So I picked a 200-meter RoPax ferry with a capacity for 900 passengers, 75 crew, and 492 cars. And again, it was modeled from the Marine Atlantic vessel that services from Newfoundland to Nova Scotia. So the principal dimensions of the vessel are length overall of 200 meters, length between principal particulars of 197 meters, molded breadth of 28 meters, molded depth of 15.5, and maximum draft of 6.62 meters. So this is the engine room I was given with my project vessel at the very beginning of second year. This is the picture of the engine room from the general arrangement. As you can see, there's one large main engine room, an auxiliary engine room, and a pump room. This is the way I designed all my systems. So to bring this up to regulation, you'd need to add a watertight bulkhead down the center line of the main engine room to create two duplicate engine rooms. And the emergency generator, which is up front, should be moved to its own separate compartment altogether. So based on this, I would have to change the designs I've done in the last 2 years, and this is how I would change my design project. So this is my ballast system. Well, I did include 2 pumps for redundancy purposes. Both are in the same engine room, meaning if the ship loses this compartment, it would lose the entire system. If the engine were to be split with the watertight bulkhead, a duplicate system would be put in place in the second engine room, creating redundancy in the system and separation of the system. This is my bilge system. Again, I did include 2 pumps in my main engine room, and this time I did include a second pump in my auxiliary engine room, covering both the redundancy and the separation. However, when the engine room is split, again, a second system would be put in place in the second room so that in an emergency situation, it could have full capacity of pumps, not just an emergency pump. This is a detailed drawing of my cooling system. As you can see, I have duplicate systems set in place for 2 engines and for my generators. So this is designed duplicate systems so that if a bulkhead was added in the center line, both engine rooms would have fully functioning cooling systems for its respective engines. This is my fire system. Like the bilge system, I included 2 pumps in my main engine room and an emergency pump in my auxiliary room, covering both redundancy and separation. When the engine room is split, again, a duplicate system would be put in place so that the full capacity of the fire system could be used in the case of emergency if we do lose one of the engine rooms. And this is my lube oil system. So based on my engine guide, the lube oil system required an independent system for every engine, including its own pumps. So that if loss of one engine, you wouldn't lose a set of engines, you would just lose the one. Meaning when the watertight bulkhead is added in the center, you would have 2 engine rooms, all systems could still run independently of each other, creating redundancy and separation. So this was my designs. Thank you for listening. I can answer any questions you may have. Yes. So for the exhaust layout, in this ship, I was only given 1 casing, so it wouldn't really meet the separation requirements, as both with the openings for the exhaust going up would all meet up into one casing anyway. So a second casing would be added, so they would have independent casings, independent exhaust systems, so that if you were to lose one and one would flood, it wouldn't potentially flood into the next engine room. Thank you. Any other questions? Yes.
Knowing that the water's up in the water, any consideration around the station
So I didn't really look at ice when it comes to this vessel. I know when, like, if it were to go somewhere else, you would have to look at those regulations. I know one of my other classmates, looking at things like the bilge system or the cooling system, had to have measures in place to get rid of the ice in, like, the sea chests and any water being pulled in from overboard. When we actually visited New Dock, we saw one of the ships had the strainer baskets, so they could pull up the strainers and clean out the ice. That's about as far as I went into the ice conditions with this vessel. I didn't go very far into that with this one. Thank you. Thank you all for listening.
Thank you, Bethany. We're a little ahead of schedule, but that's okay. We're gonna break right now, and just to keep with the schedule we posted, and reconvene at 10:30 and start up the next session of presentations. Do you have any? All right, thank you, everyone. We'll see you after the break. That's going to be at 10:30 this morning. Kate. Kate, were there any online? Okay. We have Robert Kelsey. He's doing a exploration support vessel, and I'll let you introduce your project vessel. Thank you.
Thank you, Ian. Like Ian said, I'm doing a 70.5 meter exploration support vessel. We'll jump right into it. So to start off, this presentation is the overview. We're going to start out with an introduction, give some little bit of insight on the mission profile that was used for the whole development process. Then we'll jump into the state-of-the-art analysis, talk about some of my complications I had in my design. Then we'll get into the whole form and development, talk about where the inspiration from other vessels came from, jump through the general arrangement, give you an idea of where things are located, and kind of the flow, everyday life of the vessel. Following that, we'll get into the power and propulsion, speak about the power plants on board, as well as the propellers and other propulsion. After that, we'll jump into the electrical design. The electrical design, we'll talk about the gensets. Then we'll do the structural design, talk about all the scantlings that we did, the process we used. Talk about the capacity plan. It was a key component to the design of this vessel. Then we'll get into the trim and stability, talk about how stable it is at sea in each different condition. Ending it with the estimation build cost. So to start off, quick introduction. Like I said, 70.5 meter exploration support vessel. This vessel will be owned by Bull Marine. They're based down in Louisiana. The scope of their business model is to charter out vessels to various industries such as oil and gas, research, military. So this will be part of their fleet, looking towards the research sector and possibly the super yacht division. Couple features, this vessel will be flagged under the U.S. With that, it'll be stationed in Honolulu, Hawaii as its home port. The reason why is because it's the closest port to the South Pacific Islands, still staying within the U.S. Features that drove the design, it has a speed of 14 knots. That was a deliverable we had to follow from Boulder Marine. The range, 6,000 nautical miles, and able to get out to the exploration or research vessel and return back to port to pick up more goods. Have a dead weight of 1,700 tons. Sorry. Like I said, the mission is to transport scientists, guests, equipment, fuel, provisions to the research vessel, or its second operation is to act as a support tender for super yachts. So starting with the state-of-the-art analysis, we compiled the data using an online database called Clarkson's. We were able to select various vessels out in the industry, find their given data, put them into a spreadsheet, and we were able to, like you see here, get these graphs. We can play with the dead weight that we are required to carry, and that'll give us displacement, length, beam, draft, various particulars. As you can see here, two trends that I pretty much based my design off of was the dead weight versus displacement is a very common graph to look at when designing, and also the dead weight versus length overall. That really drove the length of the vessel. One complication that I came across when I was compiling my SOTA was there seemed to be a large gap within the data between OSVs and yacht support vessels. The reason why is because my vessel, the way it was designed is to be almost a hybrid between yacht support vessels and offshore supply vessels like oil and gas. The resolution to this was I did some further extensive research, and to find closer related vessels, this took a little bit more time, created my own SOTA graphs, and took a little bit more time in the process, but I ended up finding particulars that worked out to be fitting. After the SOTA was completed and a proportions analysis was completed, the particulars that were decided upon were here as given. Displacement of 3,500 tons. It's going to have a length of 70.5 meters, beam of 15 meters. The big driver with the beam was actually the working deck space. I knew from the start of the design that I wanted to carry 2 shipping containers in the center and 2 tenders on either side. So looking at some different various tenders and widths of shipping containers, plus access around all 4 of those, that kind of drove my beam, making it a little bit wider than or a little bit larger length to beam ratio than typical supply vessels, but it ended up working out okay. It also gave us a depth of 8.5 meters, draft of 5 meters, which gives us a freeboard of 1.4. Sorry, that's not right. That's 3 meters. I think my 1.4 was the original freeboard that I changed. The reason why is because after looking at current research vessels, I realized that their freeboards were increased a little bit more, and I wanted to kind of match their freeboard for transferring containers and provisions back and forth. Lastly, the block coefficient ended up turning out to be 0.65. Next, for the hull development, talking about when I break down the hull development, I broke it down into a bow section and a stern section. For the bow section, I was trying to follow a partially inverted plumb bow. The reason I went for this is because it provides increased buoyancy at the fore end for accommodations, leaving you with kind of a less amount of buoyancy in the aft end, but you can ballast down and adjust accordingly. But the weight that's up forward is stationary and usually always there. For the stern form, I went with a pram stern combined with centerline skag and a flat transom. The reason why I went with a pram stern was to allow a good foundation for twin propellers, twin rudders, and a center-mounted pump jet thruster all the way in the aft end. I'll get more into the pump jet thruster in the propulsion section. As you can see here, these are 2 Damen vessels. I chose 2 different vessels because, like I said, my vessel is a hybrid between the 2. So this is a Damen research vessel. Kind of same aft configuration as my vessel would have. And then this down here is Game Changer. I'm also from the yachting industry, and I really like Damens in the way that they look. It's pretty much my driver for choosing Game Changer. So you can look at my hull form and see some resemblance between the 2. Getting into the general arrangement, we have here the centerline profile. You can see the amount of tanks down below here. I've got a lot of fuel oil I have to carry, a lot of fresh water I have to carry. With that, a lot of ballast. In between the sections of tanks, I have my engine room, engine control room. I have deck storage underneath the aft working deck, steering gear room. This first deck, which I'm calling lower deck, it has the galley, the crew mess, laundry, office, gym. And then next deck up on my main deck here is the accommodations. That is primarily for the scientists. The reason why I chose that is because it was the largest deck and I have significantly more scientists and guests than I do crew. Going in one deck above is the crew accommodations, keeping them all together with the captain and chief having their own single cabins towards the aft end next to the stairs up to the bridge, and then bridges above. So talking more specifically about the tank deck, you can see here is the configuration of the engine room, 2 main engines, 3 gen sets. We have a very large engineering workshop and also a very large engine control room. Going up a deck, up to the lower deck. Like I said before, we have a deck storage and equipment storage. The primary thought behind this was to add a space on board the vessel where you can put sensitive research, scientific equipment that can't be exposed to the elements. So you can see here, there's a hatch off to the side. Hatch can be lifted off. Submarines, ROVs, anything can be placed down below, and it can be safe, secured. In the aft end here, steering gear flat with this space here on the aft end is a swim step. The way that you access that are 2 spiral staircases down to the aft end. I know it's a little bit fancy for commercial, but like I said, it's trying to follow a game changer. Moving forward, we have the galley, dry storage, chiller, freezer, large crew mess. There's a total of 35 personnel on board. Forward to that is the meeting room. Primary thought for this was to add a space for scientists to join together, talk about briefing their mission, whatever they might need to use the space for. Across the hall, you have your laundry. Obviously, you need to do laundry on board a vessel, so there had to be a space for that. Forward is the office space. Again, it's another space for scientists to work out of. A couple of desk spaces, various types of office equipment can go in there for them to continue with their work that they're doing while on board or in transit. Across the way is the lounge. Nice space for them all to hang out. And then forward is a very large gym. I put in my mission profile, one of the requirements was for the scientists and crew to have access to a gym while on board. Going up another deck to our main deck, this is the primary working deck. We have a very large aft work deck here. Nice space in the aft end to put open equipment, helicopter touch and go pad. Forward, we have a workshop. You can bring in a full-size tender to do any servicing maintenance you need to do on board. We have my emergency gen set located on the main deck, as well as a pump room. One of the deliverables for this vessel was to provide bunkering to the research vessel while they are carrying out their explorations. So the vessel will tie up alongside, hoses can be transferred over, and pumping can continue. Forward to that, little mud room. If anyone's getting dirty on deck, nice to clean off before heading into the accommodations. Large garbage locker. My thought behind the garbage locker was to take on any garbage that couldn't be compacted or incinerated from the research vessel. We can take on board and take that ashore. Like I said before, the accommodations that are set on this deck are for the scientists, 22 scientists in total, and then a small server room up forward for electronics. Going up another deck to the upper deck, we have the chief's cabin and chief's office. He has his separate, he or she, I should say. The captain's cabin and office. And then the rest of the cabins up on this deck are for the 11 crew that are left. We also can see on the upper deck, we have a onboard hospital in case there's an emergency to the research vessel or operations of this vessel. If someone needs to be transported ashore, you can use the hospital. Now up in the bridge deck, you can see we have a forward-facing console center. We have a nice lounge space up here. Another office space. Thought behind this was for more of the crew. And then an aft-facing control center for the working deck, as well as 2 wing stations for tight maneuvering. So for the powering and propulsion, when we went and did the calculations for this, calculated total resistance at 14 knots of 428.44 kilonewtons. This transferred to the deliverable or delivered power that needed to be at the propellers to be 2,793 kilowatts each propeller. If we're moving forward, going through all of our power losses, we get to the effective power. This ends up being 3,285 kilowatts each. With this number kept in mind, we selected the engines to be twin-man V20 175Ds, each putting out 3,400 kilowatts. When we did our propeller calculations, we found the best propeller that fit our design were twin B series 5-blade, 2.5 meter, 1.88 pitch with a 0.75 blade area ratio. As I mentioned before, we have a aft pump jet thruster. If we combine this with the forward tunnel bow thruster, it gives us great maneuverability within tight quarters. One condition that this vessel will be operated is standby mode, and this is if they're waiting for the research vessel to continue out and finish their research, their exploration. They can just sit around, wait for them, shut off main engines, run off of essentially DP. It's not DP rated, but yeah, it's so they can run off both the bow thruster, tunnel thruster, and pump jet thruster, stay in spot, or for docking facilities. We moved to the electrical design. The electrical design was a thorough, not a very thorough analysis, but it was close enough to get us a good estimation for the size of gensets we need to place on board. The four conditions, three main conditions I've operated in or analyzed on were standby, transiting, and moored. With an emergency condition, obviously for emergency situations. As you can see here, the kilowatts are the outputs that will be required for each condition. With the power that was analyzed, it gave us a good understanding of the gensets. For the gensets on board, we have for the primary gensets, we have twin Cummins K38 CP. Those are 746 kilowatts each. Secondary genset, which is a Cummins K19 CP, which is 460 kilowatts. And then an emergency genset, which is the exact same as the secondary genset, keeping the parts in redundancy in case of emergency, better for the design. The reason why I chose two primary and one secondary is you can see if you add up the 746 while we're in standby is where most of our power is coming from, and that's because you're running the pump jet thruster, bow thruster, as well as the deck crane on board. And then if we're transiting, we can shut down the two primary gensets, run the secondary genset, because you can see 460 and we only need 439. And same thing for the moored condition, we can run just off of the secondary genset. Then moving on to structural design. Structure was sized using Lloyd's registry. For this design, I used a transversely framed system, considering the amount of shape that's through the hull all the way globally. It also has a single bottom structure due to the majority of the tanks on board are full depth tanks. They're deep tanks rather than just needing it down in the double bottom. With the structure, I had two complications. Complication one, there was a great span across the engine room, and I needed to find a way to split that up. The easiest resolution to that was placing pillars underneath the three girders, center side girders, breaking up the span, getting my girders down to a smaller size. And then complication two was the discontinuity and lower deck girders through the tanks. What I mean by this is you can see in this lower picture with this double deck tank, which is my fuel tanks, the lower deck girders are disrupted. At first, I tried to increase the size of the stiffeners on the bulkheads supporting either end. Realized that those were too great. So the next resolution was to place longitudinal bulkheads in way of those side girders and centerline girder. With this, it divides the tank up into 4 separate tanks, which is actually better for stability. So that's what I went and did. The capacity plan, here's a layout of all the tanks on board the vessel. The red tanks here are fuel, the light blue is ballast, and the dark blue is freshwater. So on board, I have 102 cubic meters of fresh water. This is ship consumable. This is enough to provide enough fresh water for 1 week. The vessel will also have a freshwater maker on board, so it can continue to make its own water. It'll also have a consumable 650 cubes of fuel. This is separate to the cargo fuel that was on board. And like I said, we have a freshwater and fuel cargo, which is just under 600 cubic meters of freshwater and 370 cubic meters of cargo fuel. The trim and stability, we considered the IMO and Transport Canada for stability regulations. The conditions that were ran for this vessel, I came up with a light ship, a prime light ship, and then I have 6 port departure, 6 mid-voyage, and 6 port arrival. Those 6 are broken down into the deck cargo being varied between full, half full, and empty, and the fluid cargo, which is the freshwater and fuel, being either full or empty. And that's where those 6 break down from. As you can see here on top, we have a light ship. It's no cargo, no fuel. It gives us a draft of just over 2 meters and a forward trim of 1.26. Not ideal, but with a little bit of ballast in the aft end, it will level it out. And then down here below is a, this is port departure, fully loaded. And as you can see here, just over our design draft and a trim of 0.45 degrees aft. The estimated price, I broke it down. We used simple calculations between material cost, labor cost, and build cost. For my vessel, we have a material cost of $11 million. We have a labor cost of $6 million, bringing the build cost to $24 million, including margin. And then the final price of the build is $32 million, and that is including the profit margin for the shipyard. Are there any questions? Yeah. 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 So those who couldn't hear, the question was, do we keep in consideration for the flooding of the engine room? Within the scope of our design, we used, we ran flooded lengths, which were 1 compartment standard for non-passenger vessels. So this vessel, due to the watertight compartments broken down, we can flood 1 compartment fully, and we would still have the stability needed to operate. Yes. Yeah, absolutely. So, question was a little bit more detail on the helicopter touch and go pad. So, helicopter touch and go pad is essentially a designated space on board for a helicopter to land, just enough to let the passengers depart or passengers to climb on board and the helicopter leave. To get into the regulations for a full helipad on board, you have to have the ability to refuel. You have to have increased structure and scantlings. You have to have specific personnel on board for those requirements. So I tried to divert it a little bit to keep the design simple and just state it as a helicopter touch and go pad without having to increase scantlings. Yeah. It's not. It's area of operations.
You mentioned that your structure, transverse structure, that's shape of that. Was there any analysis to compare it to use the plans?
Question about why I chose transverse structure. With the scope of the course, we're limited to time. If I could have done some longitudinal analysis versus transverse analysis, I would have. It seemed for the scope of the vessel, for the shape of the hull, it made more sense to initially go with transverse structure.
I have a question from the live stream. Can you guys hear me? Okay. So Bobby is asking, there's 3 different questions. I'll give it to you all at once. What was the main reason for this bow? Where is this operating? And what sea state was used for stability?
So I'll start with the first question. The shape of the bow. The main driver was I like the way it looks. I like aesthetics. So that was the main driver. But I also looked at supply vessels and support vessels in the industry. And a lot of them either had a straight vertical bow. Put that turn back on. Vertical bow or a slightly inverted on itself, or a little bit more of a traditional. For the area of operation, like I stated, it's in the South Pacific Islands, based out of Port of Honolulu. And the third question.
I can repeat it. It's okay. What sea state was used for stability?
Yeah, so for stability, the primary scope of the course is for statical stability. We didn't really touch on dynamical stability, so wave-induced. We did do a little bit of analyzing on wave-induced and wind-induced, but not specifically to certain sea state. Thank you.
How do you do that?
Something that's hard to do with such a
You don't have to talk.
can't do the process.
Ready?
Yep.
All right, the next presentation is Jordan Hartree, and he's a 3rd-year Marine Systems Design student. And Jordan, his vessel is a 101-meter dive support vessel. And Jordan's going to talk about dynamic positioning 3 and how it's tested. Go ahead.
Thank you for the introduction. As like you said, I'm Jordan Hartree, third year system student, and for my final presentation project, I decided to do a topic on DP3 and dive support vessels. So before we go too deep into this, let's go a brief excerpt on my ship. So it's a 101 meter dive support vessel, like John said. It's got a breadth of 21 meters. We've got a depth of 9.39 meters, a draft of 6.39 meters, a crew consisting of 92 people, and a gross tonnage of 5,648 tons. Now you notice here, I've got what looks like, and it is, basically 2 engine rooms separated by a centerline bulkhead, and with equipment as well being doubled for both. And we'll talk into the why that's being done shortly. And here's just a little model view. We can see that it's hard to tell here, but we can see up here how there's identical venting and exhaust piping on both sides because the engine room is split in half and they're both individual isolated systems from one another for redundancy. And we can see a picture here. Again, this is just like a side view of the vessel. We can see equipment, venting, exhaust. There's a gen set, got piping, coolers, pumps here, and everything you'd see here, including the stairs and whatnot, you would also see on, say, the opposite end of the vessel. So the main topics of discussion for this presentation are we're going to discuss what DP3 is. I'm going to inform you about the DP3 regulations. And finally, I'm going to speak about how DP3 affected my vessel over the course of my term project. So first question is, what is DP3? I've mentioned it now twice, and other people have talked about DP in their presentations as well. So what does DP3 stand for? Well, first, we need to understand what the DP means. So DP stands for dynamically positioned. And so vessels that are dynamically positioned can maintain their own position automatically, like through use of thrusters, like azimuthing thrusters, tunnel thrusters, and stuff like that. So these kind of thrusters and systems are especially useful for ships that have to maintain position in a certain area, whether it's like my own dive support vessel, and some more examples that I'll talk about later on in the presentation. And this is just an example diagram here, but we can see how vessels are influenced by multiple forces. There's waves, wind, and current. Just for some, they're jostling your ship around, and we can see the many directions of motion. Like with these forces acting on it, your ship can surge, your vessel can sway, and yaw. And there's just some of them. And like we're talking about some of the thrusters a moment ago, we see here outside of the main propulsion, this vessel has tunnel thrusters and azimuth thrusters for position keeping. So what does the DP3 stand for? So the 3 in the DP3, it's with regards to the vessel's equipment class. So the equipment classes are typically identified by their worst case failure scenario. Like what are the worst consequences that can occur when your system fails? So what this means is that the required reliability of vessels with DP3 is decided by the consequences of the loss of station keeping ability. So this means that with regards to DP3, it requires the highest amount of reliability that is practical. The practical is important because they don't expect you to make miracles happen. You only have so much space on a ship, but you should try to comply with these as much as you physically can. So earlier I mentioned some examples. So one of the first examples of a ship requiring DP3 is drill ships. Drill ships have giant drills going down to the ocean floor. They also have various piping and equipment going from the ship to the ocean floor. If this vessel were to start moving around in the sea while all this equipment is in operation, a catastrophe, destruction of equipment, and millions of dollars lost. Now, the dive support vessel, we're going to skip this one right now because we're going to touch on this one later when we talk about my vessel. Next is the crane barge. Crane barge can be used for construction and maintenance. So you have your crane barge out at sea and you're doing work on a vessel and all of a sudden it starts moving around. Once again, catastrophe. Not only could you do damage to what you're trying to construct or fix, but this could lead to the loss of lives. And it's kind of a similar gimmick with the cable lay vessel. You're laying cable at a specific location, and if your ship starts moving around, you're not on target, or God forbid, you start going backwards and your cable gets tangled up. Okay, so now we're kind of just touching on what DP3 is. We're going to discuss some of the DP3 regulations that were taken in mind when I was designing my ship. So, for vessels under equipment class 3, a single failure can be classified among the following. So, any active components, such as we're talking about thrusters, your switchboards, your remote-controlled valves, and your generators, those can all be classified under failure. Any normally static component, we're talking pipes, cables, manual valves, they can be assumed to fail. The same with any one water-type compartment, which can fail from fire, flooding, and a similar thing with fire subdivision. Once again, can fail from fire or flooding. And finally, one of the ways it's defined is that a single inadvertent act should be considered as a single fault if such an act is reasonably probable. So if something could probably happen to your vessel, if such a failure could take place, you should try to account for it. Well, you should do more than try, you should account for it in your design. Now, with regards to the power systems for equipment class 3, they should be designed with the following in mind. So, power systems, you got to be divided into multiple systems. So, at the very least, you need to have 2. You can't have any less than 2. And this is done to provide redundancy in worst case scenario situations where a system failure occurs. The divided power should be separated in different spaces by a 60 bulkhead, and we'll talk about that in a little bit. And when the power systems are underneath the operational water line, they should be separated. The bulkhead separating them should be watertight. Now, with regards to the redundant piping systems, so this is for essential DP systems like lubrication oil, fuel oil, hydraulic, cooling water. What it mentions that these piping should not be routed together through the same compartments, but they do make an excerpt where if it's unavoidable, such pipes can be run together through ducts made of A60 class steel. And it's a similar kind of situation for the non-DP systems, which they include fire suppression, engine ventilation, shutdown systems. They should also all comply with the above regulations as well when physically possible. So I mentioned an A60 class bulkhead, but what is that? So an A60 class division, this is a divide formed by either a bulkhead or deck. Now, this division has to be constructed of either steel or an applicable equivalent material. And regardless of what material you use, it has to be suitably stiffened. It doesn't matter if you have the proper material. If it's not stiffened, it doesn't count. Now, where the A60 comes from is that it's able to block the passage of smoke and flame even after 60 minutes of exposure to fire testing, which is where the 60 comes from. So this bulkhead is to be insulated with materials that are non-combustible, so that after 60 minutes following a fire test, the average temperature on the opposite end of the bulkhead should not rise any more than 136 degrees above the initial testing temperature. And it's a similar situation with the Pacific area where the temperature of any specific area should not rise any more than 108 degrees on the opposite end of the bulkhead. So this could be any part of that bulkhead. So here we just have everything else taken out. We can see there is a centerline bulkhead that divides my engine room, which consists of the area above the tank top and the tween deck, and it is a watertight division, keeping the two systems most of the systems isolated from one another. So, now we're going to talk about how DP3 affected my vessel. And we can see here a centerline profile of equipment, and you'll see a similar layout if you were to flip the vessel on the other side or mirror the view. So what is a dive support vessel? Well, a dive support vessel, or a DSV, is typically used for underwater work, including like maintenance and inspection of vessels, mobile platforms. It can be worked on pipelines, their wellheads, and stuff similar to that nature. You could find them offshore doing maintenance on an oil rig, for example. And DSVs are always equipped with diving equipment. We're talking diving lockers, maybe decompression chambers, and stuff of that nature. And something else that you'll find on a dive support vessel is a moon pool, which is a hole in the vessel open to sea, where like divers, ROVs, or remotely operated vehicles can go to and from the hole to the work site. And with a DP system, a DSV can maintain an almost exact position over the work site. But why specifically is DP3 needed? Why not DP2 or DP1? So DP3 is required because if failure occurs in the system, divers are directly at risk. Like malfunctions can cause havoc and loss of life. Also, if a vessel moves away from an intended diving spot while divers are trying to move to the work site, that could also be disastrous for the divers. They could be hit by a moving ship, get caught in propellers. You don't want that to happen. So, and this is probably one of the most important reasons why DP3 is needed, however. This here is a picture of a decompression chamber. Now, decompression chambers, they need to always be functional. If divers are coming down from deep depths and they're ascending, this can lead to the buildup of nitrogen bubbles in their bloodstream. And without proper decompression, these bubbles can either lead to sickness or death. So this system requires redundancy to operate. If you rely on only one engine room and this system were to shut down because it couldn't get power, then the divers who need to use it or are currently in it could die from those nitrogen bubbles. Another system that is also pretty important is the saturation diving system, and this can provide important gases like, say, helium and oxygen to divers deep in the ocean. And so this system's got to be online, otherwise they could suffocate with the lack of air. So now we're going to talk about what DP changed for my vessel specifically, and it's a bit funny. So the format for this is kind of a before and after, because I didn't realize it was DP3 right away. And so I did like multiple systems, which I had to go back and actually fix afterward. For example, originally with my fuel oil system, it consisted of one large series of pipes, equipment, and fittings. My engine guide basically told me I could have gensets hooked up in series. And so the 4 gensets used in this vessel were connected in series for ease of maintenance and cost savings. However, after learning about DP3, that I had to separate my fuel system into 2 independent system circuits. And they were, in fact, separated by an A60 class bulkhead. And each system now consists of 2 gensets each instead of 4. And here we can see. So we can see here we have our own, each system has its own set of pumps. And we have 2 pretty much identical system circuits for the fuel oil system that are separated by the centerline bulkhead here. Next is the lube oil system. Very similar situation. It started out as a single system, a single lube with having a single lube oil, renovated and renovating tank. Also with an individual lube oil purifier. Now, after having to comply with DP3, it was turned into 2 separate systems. So 2 for a total of 2 lube oil, 2 renovated, 2 renovating tanks, and each system having its own individual lube oil purifier. So 2 in total. A crossover pipe with a gate valve between the tanks were added for redundancy, and once again, it's separated by an A60 class bulkhead. This is an absolute requirement. You can't skip out on that. And see here, so it's very similar setup to the fuel oil system. Very identical circuits with its own set of pumps on each system. Also, we can see here, this is the center line. This crossover valve I mentioned before, which allows fuel to be transferred from one system to the other in case of emergencies. Next is the cooling system. Again, I'm surprised it was a single system with 2 transfer pumps and 2 cooling pumps. The 4 gensets were arranged in series as recommended by my engine guide, and the system had 2 plate coolers. Now, after complying with DP3, those 2 systems it was separated into 2 systems, so each having its own set of transfer pumps and cooling pumps, with 2 gensets comprising of each system. So this led me to have it, in the end, a total of 4 plate coolers, 2 for each. And once again, can't stress it enough, it's got to be separated by the H60 class bulkhead. And here we can see 2 very identical systems. Here's the bulkhead that separates them. We have port starboard. We have a set of transfer pumps, a set of cooling pumps for the fresh water, and we have our plate coolers here as well. You can find them on both sides. And here is just a little mock-up model of the freshwater piping. You can see here they are independent of one another, so they don't interact. They're isolated. It's hard to see in that view, but here we can see that there's no pipes connecting from one system to the other, and they will be separated by the bulkhead shown earlier on in the slideshow. Now, thankfully, by the time I got to the ventilation system, I had wised up. I knew that it had to be designed with DP3 in mind. So this system was 2 ventilation systems, 1 port, 1 starboard, and each system receives air from a fan from the wheelhouse deck, and that fan has a pipe that feeds down to the engine room, which consists of the space I mentioned earlier above the tank top between decks. And each system provides air for 2 gensets, and these systems are once again separated by an H60 class bulkhead. So here we can see, here's the fan suction, the pipes come down. So these ventilation ducts provide air to multiple areas in the engine room for air circulation. In this view, we can see how these ducts here, this provides air to this genset. It's a little difficult to see, but this duct provides air to this genset. And we have a similar situation over here. And once again, these systems are isolated. They're independent from one another. There's no interaction. Next off, we have the build system. So build system and valve system were a little different, and we'll get into why now. So the build system was a single system located in the engine room, and the centerline bulkhead was penetrated by piping. And the equipment was also located in the engine room. Now, one of the things I had to do was the system was moved forward to a thruster compartment, along with the equipment like pump, filters, valves, and so forth. And the piping was now routed through the forward engine bulkhead to access the engine room. We can see here, we have the equipment now in the thruster compartment with the valves going to the forward engine bulkhead for the direct build suction. The valve system, very similar. It was a single system located in the engine room. The overboard discharge was also in the engine room. So to change this, the system was moved forward to the thruster compartment. The pumps were moved forward. The ballast water treatment system was moved forward, and the overboard discharge was also moved forward to the thruster compartment. So it's very similar set to the ballast system, with the a penetration for this system to the cross connect, the forward bulkhead, to get access to the seawater. And finally, we have the exhaust system. Much like the ventilation system, the exhaust system was designed with DP3 in mind, thankfully. So the exhaust pipe runs up past the wheelhouse deck. Each room has 2 exhaust pipes routed through the casing. And so the pipe consists of, we have a silencer, insulation, a drain to bilge, and finally the pipe ends with a rain cap on top. So in this image here, we can see that the red here is actually the insulation. We have a silencer, and there's a rain cap on top. And so there's 2 pipes for each engine room and 1 for each genset. In this view, we can actually see how they come down and connect here. And once again, they're isolated from one another. The casings are on, they don't connect. There's no interaction. So thank you for listening to my presentation. Any questions? Yes. Oh. Okay, who wants to go first? Okay. 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 So the way that it was for redundancy. Now, it wouldn't be used in emergency situations, but let's say that a pipe breaks or some lube oil gets contaminated in one tank for that, like for the port tank to the port system. By using that crossover pipe, I can open the valve. I can close the valves to that tank, open the valves on the crossover, and I can feed the lube oil from the starboard tank to the port system. So that way I can still change the oil in case it malfunctions, at least long enough to fix the system. And with the way the valve is, the valve will be placed against, say, the bolt flush to the bulkhead, so that for emergency situations, it could be shut down to halt the flow of any flow. I'm actually not sure. We didn't have to run any calculations specifically for like how the DP3 would operate. It was more so complying with the redundancy for it. Yeah. Oh, yeah. Yeah, and that's a good question. So bilge and ballast, right? So I had to move them to my thruster compartment for space constraints. Once I learned I had to do DP3, that meant that a lot of my equipment had to be doubled. So my engine room became very tight on space. I could physically fit all the equipment into one in the engine rooms, but there would be no room for anyone to walk around, let alone do equipment, like maintain piping or equipment. So what I did for those systems, like say the bilge system here, there are valves flush to the bulkhead going to the suction for each engine room. And so in case of emergency, say there was a fire or a flood here, this valve on the thruster compartment side could be closed and therefore ceasing connection to this engine room, but this valve could be left open so you can still supply you can still get direct suction from the opposite engine room. And it's a similar situation with the, with the ballast. That's ballast. So a similar situation with the ballast system where the connection to the cross connect in the engine room has a valve on the bulkhead, which can be shut off for emergency situations, for any sort of fire or flooding in the engine room. Yes.
What do you do in case your compressed air system?
So the compressed air system was also moved to the thruster compartment, and a similar situation where pipes were feeding into the engine rooms were done. Yes. So yeah, the compressed air system was a single system, but moved to the thruster compartment, where the thruster compartment is not divided like the engine room was, and I just used valves similar to this setup where you have valves going into the bulkhead in case shut off had to occur in emergency situations.
What flaps that practice? Sometimes that.
There were valves also around the engine room, so you could shut them off there as well, like worst case scenario, like valves around the gensets for compressed air. Yes. I'm sorry, what? Oh, 1 second, sorry. Yes, they were calculated to provide enough power. So one could provide power to, position keeping or motion, while the other could still provide auxiliary power to the ship if needed. Pardon? Yes, of course, yeah. Thank you. How do I get out of this? End show. Okay. Pretty cool flash drive, huh?
Just trying to get this adjusted because it's. Check. Hello? Okay. So just a step closer to get the mic to work. I was getting feedback there earlier, so I just adjusted it. But it's a little too big. Okay. Just give me this. Just a nice point. All right, thank you, Jordan. Up next, we have Madison Gregory. She's going to be doing her project vessels on a 3,600 lane meter RoPax ferry. I'll let you take it away. Thank you.
Spoiler. My name is Madison Gregory. I chose to do naval architecture because I would consider myself a pretty creative person, and this program allows me to really dig my feet into that. For my senior project, I chose to design a 200-meter Marine Atlantic ro-ro ferry. So the contents of this presentation is the mission profile, SOTA, hull development, general arrangement, powering, structure, capacities, trim and stability, price estimate, and summary. So the mission profile is the first step in the ship design process. The purpose of this is to generate a clear definition of the design objectives. It outlines the features and parameters required for the vessel to hit all design objectives. So why did I choose to design a Marine Atlantic ferry? A consistent and reliable ferry service between Newfoundland and Labrador and the rest of Canada is and always will be essential. When Newfoundland joined Canada in 1949, we were granted special constitutional status that actually mandated the ferry service between us and Canada. Marine Atlantic's current fleet are reaching the end of their useful lives. They're going on 20 years old, and they'll soon need to be replaced. A new ferry is necessary to carry passengers and cargo between North Sydney and Port aux Basques in an efficient, safe, and comfortable manner while maximizing profitability throughout the vessel's life. The design constraints for this ferry were motivated by space restrictions at North Sydney and Port aux Basques ports, as well as customer demand. The first restriction is the length was restricted to a maximum of 200 meters due to space limitations in Port aux Basques Harbor. This island is essentially the cause of the problem, and Marine Atlantic recently purchased this island, and they intend to dig it up in the near future. The vessel has a minimum passenger. The vessel must have a minimum passenger and crew
capacity of 1,000 and at least 3,000 lane meters to meet customer demand. The vessel must also be able to make one round trip a day. This constraint not only affected the speed, but I had to ensure that the vessel was designed in such a way to minimize time required to load and offload vehicles. And finally, the depth of the water in North Sydney is 7.4 meters, meaning the draft of the vessel could not exceed this, and consideration was given to low tide situations. With the design constraints in mind, the operational profile for the vessel is as follows. So it is to primarily operate between North Sydney and Port aux Basques, which is 98 nautical miles. And it's also able to do the Argenta run if it's needed. The endurance is 28 days, range is 5,400 nautical miles, and the turnaround time at port is designed to be between 4 to 5 hours. It will take the vessel 6 to 8 hours to travel from point A to B. So with the amount of time it takes for the vessel to travel from point A to B twice a day, and the 4 to 5 hour turnaround time should allow the vessel to do one round trip a day. Some less interesting but still important details from my mission profile was that it is to be classed by Lloyd's. It's constructed at Victoria Shipyards. Maintenance and repair work is done at Irving Shipyard in Halifax, and it will fly a Canadian flag. So next up was the state-of-the-art analysis. This process is essentially the translation of mission requirements into preliminary ship proportions. It is a parametric study of ships with similar proportions to the vessel being designed. While collecting data, I was able to find similar proportions for 88 vessels. 88 vessels with similar proportions. Out of the 88 vessels, I was only able to find 12 of them with displacements. This made determining this parameter challenging, and it was later verified once the rest of the parameters were determined using displacement equals length times speed times draft times density. Then this data was compiled into graphs. Initially, when I did this, I found that I had a lot of clustered data points, which is compromising the accuracy of my analysis. Upon further investigation, I realized numerous vessels in my SOTA were sister ships. So essentially, it was the same ship in my data over and over again. Once I removed the sister ships, relationships between the parameters were much more linear. So I did this process a lot of times, comparing a lot of different parameters. Rather than going through them all, I'll just put them here. So the results were an overall length of 197.5 meters, a waterline length of 188.8 meters, displacement of 21,686 tons, dead weight of 8,500 tons, draft of 6.7 meters, speed of 16 knots, lock coefficient of 0.61, and a depth of 9.5. So next was hull development. This is a very important part in the design of a vessel, and it directly impacts the operational profile and performance of the ship. The hull for this vessel was designed using a program called MaxSurf. Some characteristics of the final design was that it's a displacement type hull, meaning that the Froude number is less than 0.4, is actually 0.19. It was designed with a large parallel middle body to maximize cargo carrying capacity. I ensured it had smooth lines to minimize hull resistance and operational cost. It was designed with a normal bow for most efficient operation and a stern with sufficient space to support the vessel's twin screw arrangement. Then using the lines from MaxSurf, I was able to set the station and buttocks line spacing and generate the line plan for the vessel. A question I got asked a lot is, why don't I have a bulbous bow? So this graph is from the Watson's book, Practical Ship Design. So it's evident that a vessel with a Froud of 0.19 and a block coefficient of 0.61 would be most efficient with a normal bow. Since the hull is full and moving at a slow speed, a bulbous bow would only add resistance. Next is the general arrangement, which is essentially a blueprint for the vessel. It includes basic layout and arrangement of ship components and compartments and guides the designer in creating a functional and efficient vessel. Starting with the centerline profile, the vessel has a total of 8 decks, including 2 decks allocated to machinery, 2 railroad decks, and 6 accommodation decks. Next is the tank top. My tank top is 2.6 meters above baseline. It features fin stabilizers for passenger comfort, 2 bow thrusters, and the machinery space is located aft to accommodate the direct drive shafting. One interesting feature of my arrangement was that I had a lot more space than I knew what to do with. However, this is common for these types of vessels. Next is deck 1, which is a tween deck. It's 6.7 meters above baseline and is home of the steering gear compartment, electrical workshops, stores, and the ECR. Deck 2 is the lowest vehicle deck, also known as the bulkhead deck. It has 1,970 lane meters and is slightly larger than the deck above. And the chain lockers are located on the fore and end port and starboard. Then deck 3 is the upper vehicle deck, also known as the weather deck. It is 15 meters above baseline. It has 1,670 lane meters. The windlass is located on the fore end, port and starboard, and the emergency generator is located on the fore end on the port side. Deck 4 is the accommodation deck and will be the most high traffic. I designed the layout with this in mind, with wide passageways, many amenities, and with a simple layout. So some of the design features were accessible cabins on this deck since it's the lowest accommodation deck. The galley for the restaurant is located next to the galley. There's office space, passenger galleys are twice, and mooring equipment is located on the fore end. The amenities on this deck are the kids' playroom, arcade, theater, gift shop, bar and lounge, restaurant, passenger seating area, reception, and buffet. Accommodation decks 5 to 7 are much the same, consisting of mostly passenger cabins. There's outside seating on deck 5, 8 150-person lifeboats, 203 passenger cabins, 20 allocated double occupancy crew cabins. There's laundry facilities on each deck, and the crew mess, galley, and lounge is located in the vicinity of the crew cabins on deck 7. And last but not least is the bridge deck, where I have the AC compartment, a laundry facility, 6 double and single occupancy officer cabins, a spacious bridge, captain, engineer, and chief mate rooms, and it is 31.7 meters above baseline. Next was the powering. It's important to estimate the powering requirements early in the design process, as it can have a large impact on performance, efficiency, safety, regulatory compliance, and alignment with client requirements. So the propulsion arrangement I chose was a direct drive medium speed diesel engine. I chose this because they're very fuel efficient at cruising speeds. They produce lower noise and vibration, and they have a long service life. They're also known to be more reliable than diesel or electric, which is important when you consider how how essential the ferry service is for the province. Then for the transmission, I chose diesel mechanical. It's lighter and less expensive than diesel electric. It's more durable and dependable, easier repairs, meaning faster repairs, and 98 to 99% of input power is transmitted to the output shaft, so it's very efficient. And finally, for the propulsor, I chose a twin screw arrangement with a controllable pitch propeller. The twin screws offer better maneuverability, especially for the Port of Basque Harbor, and as well as redundancy if one system fails. The controllable pitch propeller offers excellent maneuvering characteristics, which is also important when you consider the ports that this vessel goes to. To select the main engine, we used the Holtrop-Amended method, which is just series and regression equations. So I found the total ship resistance to be 278.6 kilowatts. The propeller diameter was calculated to be 4.8 meters, and there was a required power output of 5,455 kilowatts for each engine. So the Wärtsilä 10V31 medium speed diesel engine was chosen, which has an MCR of 6,100 kilowatts. To select the gensets, we did an electrical analysis on the vessel. So we created a single line diagram and separated the essential loads from the non-essential loads. We use load factors to calculate the amount of power required for the vessel's three most common operating conditions, which for me was in transit, at port, and emergency. So the power required in transit was calculated to be 1,560.2. At port, it was 759.2 kilowatts, and emergency was 764.3 kilowatts. So the main generators selected are the Wärtsilä 12V14 with an MCR of 910, and there's two of those. And the emergency generator selected is the Wärtsilä 4L20 with an MCR of 800 kilowatts. Next was the structure. Structure is fundamental for ensuring safety, efficiency, durability, regulation compliance, and overall performance of the vessel. The scantlines were calculated using Moy's rules. The steel material was chosen to be Lloyd's Grade A. The vessel is longitudinally framed with transverse framing at the ends. And it is Lloyd's Grade A, Lloyd's 1A ice class. So this is my 3D structural model. One of the issues I ran into with structure was that the spans of the girders were too long, and it interrupted, and they were too big they were too long, and it would have intersected the tallest transport trucks that entered the ship. So I had to come up with a way that I could reduce the size of these because at that point in the design, increasing the deck height wasn't a feasible option. So I had to add pillars to the center line of the vessel, which unfortunately interrupted the continuity and efficiency of the vehicle loading and offloading a little bit. If I could do the design again, I would look at increasing the height of the vehicle deck, maybe a meter. Next is the capacities. So capacities basically refers to the volume or storage capabilities of various tanks and compartments of the vessel. This impacts the ship's operational range, stability, cargo carrying, efficiency, and compliance with regulations and economic viability. So I found that my vessel was required to have 753 tons of fuel, 4.4 tons of lube oil, which were both calculated based on the consumption rate of the engines, the engine and genset power, the number of hours the engine is operating each day, and the range of the vessel. Next, the dirty oil was calculated to be 4.6 tons, which is, as a general rule of thumb, is lube oil capacity plus 5%. The fresh water is 882 tons, which is calculated by the number of passengers or crew times 0.12 tons per person times the number of days. I'm required to have black water capacity of 397 tons, which is 45% of the potable water capacity. 485 tons of gray water, which is 55% of potable water capacity, and 3,420 tons of ballast water. The ballast water is probably the most challenging to estimate since there isn't really an equation for it. So I estimated it by analyzing ballast capacity of similar vessels, and it was more of a trial and error thing when I did the stability book. Then for the cargo capacity, the payload on ro-ro ships are combined of vehicles, which makes this a little bit more complicated. The weight of cargo may vary for each trip. So the vessel has a dead weight of 8,500 tons and 3,640 lane meters. After subtracting the weight of freshwater provisions, passengers, etc., 6,295 tons of dead weight remain for cargo. So to check if my ratio of dead weight to lane meters was reasonable, I determined the average length and weight of the three most common vehicles, car, truck, and tractor trailer. And I generated a series of possible loading scenarios for the vessel. For example, 100 cars, 50 trucks, and 80 tractor trailers. I found that there's generally excess dead weight remaining once the vessel was full, maximizing the vessability of the vessel's payload based on demand. So basically, if the car, one trip the vessel may be filled up with cars, or one trip it may be filled up with transport trucks, but either way, it should not exceed the vessel's carrying capacity. Then was the trim and stability analysis. Good trim and stability characteristics are very important, especially for passenger vessels. Trim and stability investigation makes the vessel much more comfortable, safe, and more cost efficient to operate. The following loading conditions were investigated using GHS, our light ship, port departure, mid-voyage, and port arrival. I found that out of these four, port arrival was the worst operating condition. We also did analysis on the effects of wind healing, which was quite large on my vessel because of the area of the superstructure, and passenger crowding to ensure the vessel could withstand these emergency situations. And these are some of the stability graphs that were generated using GHS, upright hydrostatic curves, max VCG, and cross curves of stability. And then finally was the price estimate. Cost estimation is important as it assesses financial feasibility, efficient resource allocation, and competitive bidding. It can be very challenging to get an accurate estimate, especially early in the design. To generate the cost estimate for the vessel, Carriot's method was used. This involves a series of regression equations for estimating each category of costs associated with building a ship. So, on the left, I have labor costs, and on the right, I have material costs. So outfit labor was $8,334,509. Machinery installation, $601,561. Steelwork labor was the largest at $15,131,212. Outfit material, since it's a passenger vessel, was also large, which is $4,840,576. Machinery plant material is $8,413,217, and steel material is $2,423,211. So the total build cost of the vessel came out to be $64,959,757. So that's the cost to build the vessel, including materials and labor. And then assuming there's a 30% profit margin added to the vessel cost, the ship owner would pay a total of $84,447,684 for the ship. And that's the end. Any questions?
Excess amount of space.
So the reason for that is because I found that if I took my lowest vehicle deck any lower, the curvature of the hull started making it, the fast changing hull made it not feasible to put vehicles down there. I would have put a whole vehicle deck down there just to fit a few cars. So the depth ended up being higher, resulting in more space below in the hull.
I have a
Yep. I briefly looked at the Argentia port, and from what I could see, it looked like the vessel could dock there successfully. As for range, it wouldn't have such a long endurance if it was frequently going back and forth between Argentia, but it could do it for a short period of time if it needed to substitute it for another vessel.
I have a question from the live stream. So Bobby is wondering, he says, Marine Atlantic enters Port Basque and does a 180 and backs into the dock to unload. How is this possible without a bow thruster?
The vessel actually does have bow thrusters. I must have missed that. And I apologize for that. In the video, actually, here you can see them. You can't see them very well, actually. But they do have 2 bow thrusters on the forend.
He also has a follow-up. He says, what type of bow door do you have for loading and unloading?
So the bow door would be, it opens out like wings. If I could go back, I would probably do a visor type bow door, because I'm not sure how much width the vessel would have at port. But in saying that, it's hard to find a lot of research on bow doors. There's not a lot of information out there. The Nazi-Pi system is not something that I looked into, but it's something that I would do more research on if I were to do this another time.
Thank you, Madison. Well, that concludes our morning session. We'll break again now for lunch, and we'll reconvene again at 1 o'clock to finish off the last of the presentations. Thank you.
Supposed to be green? Okay, okay, here it is. Sorry. So, the last of the Marine Systems third years is Mr. Mehdi Khan here. He's going to do a 105-meter Arctic Offshore Patrol Vessel. Mehdi, take it away.
Thank you, sir. Hi, everyone. As Sir John Lee mentioned, my name is Mehdi Khan. And my project vessel is a 105-meter Arctic OPV, which is an offshore patrol vessel. But as a system designer, I'll be talking more about a selected system of this vessel. So technically, I'm also looking forward to explain how I went through the component selection process and some other designs through my vessel. So from the time when steel ships came into use, the design process has changed within ships. Some of the things that I wish to review with you all is, like I said, the pump selection process, a component selection process. I want to go through a rough estimation while making those selections. A system overview, I'll be selecting all of the ship design and then go through, see how that works. A 3D model of the system, and then see an efficiency check, a small efficiency check of our system. We also want to go through a spool design outlet, like during our 3D model design, we want to see how the pipe layouts have worked out. Fluid simulation, we'll be selecting all the spools and see how fluid behaves in that spool. And a small aspect of future system design that we are expecting in the near future, a change that we might expect. So as mentioned, steel ships have changed the design aspect of modern system design. The ironclad from the 1890s is one of the categories. And because of steel hulls, we want more powerful propulsion, which we used from the earlies was the external combustion engine or steam engine, which would power our propellers in this while you're using steam hulls or steel hulls. Ships are basically designed on the three categories. So we want to explore, so we make exploration vessels. We want to export commerce or merchants, or for warfares. And still today in the modern generation, with the development of technologies that we're having, right now we want to dream bigger. So we want to explore farther and more deeper. So we make much more advanced technological vessels. So we still, for exploration, we advanced in our technology and development. We want to export more goods and generate more revenues in a shorter period of time. So our commerce has developed too. And of course, we want to protect our national interests. So military vessels has evolved within time. So the three categories hasn't changed, but it has given birth to a whole discipline of in the maritime industry, which we call marine system design. And as mentioned before, I'll just try to pinpoint that. We'll be talking about systems in the ship. So as a maritime system designer, we have to deal with certain aspect or operational conditions that the ship systems operate. Some of the systems like the bilge system. Then we have the ballast system. We have the fuel system. We have the sea and freshwater cooling system. The leave well system. So these are some of the basic necessities that contemporary steel hull ships have. But we'll focus more, like I mentioned, we will select one of this design and talk more elaborately to find out how component selection can take place, or how components in a system is selected. So in order to do that, we will choose the sea and freshwater cooling system. And we will try to talk more about how we can make a pump selection in the system and make sure the pump is efficient and it's working. And when we finally distribute the design idea to our, let's say, our ship owners or clients, we want to give them the best of the results that they want from our firm or from us as a designer. So to understand the system itself, we must understand the nature of our ship. We must appreciate the nature of its operation. It is a 105-meter Arctic offshore petrol vessel, as mentioned, and it has a crew member with 23 souls on board. And its total installed power is 13,260 kilowatt. And this power will be provided by 3 gensets working together. And the 4th genset will be on standby. Each of these genset has a total power of 3,920 kilowatt. So 3 of them working together during ice-breaking conditions will provide the ship its operational profile to operate in extreme situations like that. So to design our seawater cooling system, we must keep the extreme situation in mind so that when the ship is out there breaking ice, it can perform as expected and the engine doesn't overheat. To begin our seawater cooling system, the first or best place to look at is the engine guide itself, because it's the engine that we're trying to cool. The engine guide is a perfect source for most of the information that are required. Per se, it will give the idea of how much flow rate is coming out from the inlets or how much heat will be produced or emitted from the engines itself. So the engine guide came out with a diagrammatic for each of the genset working and to what kind of components it requires in order to operate or cool down for an external cooling system. Using that diagrammatic out there, we incorporated 3 gensets working together and made a diagrammatic of our own as designers. And this is where the expertise that marine system designers are expected to perform. We can interlink one entire function with 3 gensets working together. As you can see, the emerging and diverging pipes, we have to take into account the velocity of the fluid and ensure that when our pipe emerges or diverges, the new inside diameter does not interrupt or impact the velocity that the engine actually requires. The engine gives us an idea of how much velocity or how much flow rate we expect to keep in a consistent manner. And that's how we have to develop the system. So we have to make sure that by using when the pipes are emerging together, the new inside diameter can incorporate those requirements. A small overview of how the seawater cooling system works is quite very straightforward. Hot seawater will be coming out from hot fresh water or hot coolants per se from the genset will be coming out from the outlets, and they will be going all the way towards the plated heat exchanger right there, where they will face or exchange heat with cold seawater. And then once those coolant or fresh water is cooled, they'll go back to the inlet and back to the engine. And this cycle continues, making sure that we have the optimal temperature required for a very efficient engine or our genset for this system. And as I mentioned before, to keep the inside diameter as required by the engine, we used this formula here, which is Q is equal to mv square, or flow rate is equal to pi r square into feed velocity. And you use this r, which is the inside radius. We can convert that into diameter and find out the inside diameter for every emerging and diverging pipes. But today, for the purpose of component selection, we'll be talking mostly about the seawater cooling pump right there, and how we can select an engine, a pump from a vendor, what kind of steps we have to understand, or what kind of calculations or measurements we have to take in order to select that pump. So first of all, before the information that we can send to our vendors, and so that the vendors can understand what kind of pump we're looking for, we must have the pump flow rate calculation and the pump head. And then we can send it to our credible vendors, per se DESME, GOES, or Pump Plus, who are distributors. During our initial design aspect, we do not know the location of the pump. So we took a total static head to be from the tank top all the way to the upper twin deck head. Our pump could be anywhere from here. So during the initial design process, to understand the nature of our pump, that's the static head we took. And for the flow rate, like I said, the engine guide is the best place to look for sources. We can see that the capacity of engine-driven pumps inside each engine is 75 meter cube per hour. And there's two of them. One is for the high temperature cooling water, and the other is for low temperature cooling water. And if we incorporate 3 gensets working together, the total flow rate for the 3 gensets will be 450 meter cube per hour. Again, the engine guide has a requirement. The seawater flow rate that will be cooling down that fresh water must be 1.5 times much more than the fresh water. So our seawater flow rate will be 675 meter cube per hour. And our pump must be capable of providing this flow rate. And that is the flow rate for the pump. Like I mentioned, this is a still initial design stage. We still do not know much where the pump is located. So to take into account the dynamic head loss of the pump, we used Darcy's equation and a fluid velocity of 4.6 meter per second from SAMI, and the pipe length of 4.61 meter. We still have not designed the pipe layouts for the system, but then how can we get something, a figure of 4.61? We assumed it from pre-drawn or similar vessel 2D model designs. And then we get total static head of 12.9 meter. And we send that information to DESME, and DESME comes up with a pump graph saying pump efficiency, our duty point lies somewhere here, and 250-310 is a perfect model for now in the initial design process. And they gave us a quote of $48,000. So to keep that in a point, like now we have something to work on. Now we have something to show our client or farm or our ship owners where the system is going. We have a pump now to work on it. So once we get the pump and the model of the pump, we finally draw a 2D model, and we finally find a location where we can install the pump, and then take the actual measurement of the before that the value that we assume 4.61, we can now measure it. But with technology evolving, we can now step into a 3D model. And a 3D model will give us a better visualization of the entire system. Our plated heat exchanger is right there. Our seawater cooling pump is right here, the one we selected from DESME. And now the 3D model that's provided by DESME also gives us a idea of space reservation that we need for the ship. And using the 3D model, we can measure the actual length that we assumed before, which is 5.73, and the old value was 4.911. We're getting more accurate now as we develop our model. Not just that, we can also take into account the long radius elbow and the long radius elbow of the whole system. We also have a T right here, so you have to take into account of the friction loss that's taking place here. And of course, our basket strainer and our butterfly valve that we have incorporated in the system. So we list them up, find out the total L by D, or length by diameter ratio of the pipe fittings, get the total friction factor for both fitting and the pipe, and use that value. Remember, we got the new L value or the length value by measuring our 3D model. We use that and finally calculate the total friction loss factor. And using that, we get a total head of 7.54 meter now. Now that's very low because, as I mentioned, we finally know the location of our pump, and the static pump head is now 3.3 meter, which is this, and the 4.24 that we calculated from our 3D models has shown us that our total head requirement is only 7.54 meter, not 12.93. So now our pump duty point is somewhere here, and our previous pump model was here. We are no longer efficient. This shows that a $48,000 pump in its initial design process of our system, if we bought it, we would have made a major mistake and would have proven inefficient in the system. Now we know that we need a new pump, and we can propose the idea of buying a new pump for the system. So we go back to our vendors again. We send our information to DESME, and DESME, using their software or pre-installed software, you cannot even know what new pump you need. We have the new DSL 300 and 320 FG model with a net positive suction head of 1.66 meter. And this duty point is aligned with this efficiency. So this pump is something we can use now. Unfortunately, we could not get a price estimation of this, but we went to a similar, we sent the similar information to Golds or Pump Plus, and they sent it to Golds, and they gave us an informal pricing of 40,000 USD per unit. I must keep that in mind that even though the price is lower now, $8,000 lower, but the new pump that we got is not certified by Lloyd's, which DESME offers in its pricing. So even though it's a lower value, just because we want, as a maritime industry, we want our regulatory bodies green flag before purchasing equipment, something like that from Golds or Pump will not do the justice. So I'm still waiting for the new code from DESME. Speaking about component selection, how else can we use this 3D model? Like I mentioned, I wanted to show some of the spool designing segment or pipe layouts of my 3D models as well. If you notice right here in my pipe layout, there's a bent spool. And this happened because there was a vertical misalignment with my temperature control valve and my cold water inlet. And at that point, as a designer, I was in a dilemma whether I should use a 45-degree elbow or should I go for a bent, or should I go for a bent spool? And am I saving more money on the bent spool, or am I having a better efficient 245-degree elbow here? And that's something I had to pick up. And taking that spool into consideration, and I'll show you the design of my 245-degree spool as well. So which one would work better in this situation? To find that out, I put them into a simulation software. I used SimScale for my software of choice, only because it was easier and faster to learn and use. SolidWorks is more efficient to show you even and to give more boundaries and parameters of your simulation. And in this simulation, if you look at it, for the bend pipe, what we expected, right at the bend points for the spool, there is more pressure growth. And it's happening because the way I explain it is because of Bernoulli's equation. When there is a difference in pressure or difference in velocity or velocity drop, there's a high chance of having high pressure. And because of the pressure differences, we can have cavitation here that will eat away the pipe slowly. And for the 45-degree spool, right, that we used, 45-degree elbow that we used to design that spool, this was surprising for me as a designer because I expected a smooth flow in my velocity, but there's a turbulence here. And I did not acknowledge, or I did not know why it was happening until I went back to my 3D model, and I found out not only did I have a vertical misalignment, I also had a horizontal misalignment. So the spool that I designed by drawing a circle and then extruding it through a certain path line, it was curved. And that's for the small amount of curve, we have more turbulence here, causing this disruption here. But it gives us a general idea of how fluid flow can happen in spools. So what I wanted to review here was what we spoke about, pump selection process, as rough estimation that we used our technology for, overall system overview of our seawater cooling system, the 3D model of the system that we designed of our seawater cooling system, and the efficiency, like was the system efficient, or what the next step should be. Spool designing, now that we have seen a simulation, the best thing we can do next is understand the cost pricing of fabrication, since 45-degree elbow was much more convenient for future uses because cavitation will be less comparing the bend spool. We can go with that, and we can make new estimation of our cost prices from there, from our vendors. Speaking of all this technology that we have used, and speaking of marine system design, I wanted to finish by just talking a few things about the future of this system designing process. So future will be obviously artificial intelligence will have a huge impact in this industry. All the new builds now are coming with a digital twin of their own, and digital twins come with all the systems and components, even the pipe layouts. So if you want to walk around the engine room and see your space reservation, that's completely possible. Not only that, now that the new build engine room has all the sensors will feed in information and send it to a cloud-based storage location where our AI or our system can input data and use that data for future maintenance and make an estimation and logistic for all the necessary changes that ship needs to go through in its life cycle. These are convenient for our future automated vessels that are coming. With all the industries, our industry will also be affected in some way with artificial intelligence. We tried for a bit of humor's sake, we tried sending this information to ChatGPT, which is now a global celebrity at the moment, artificial celebrity, as I can say. I asked ChatGPT to make me a seawater fresh cooling system, and it came up with a huge bunch of logistics that we can go through. It told me how seawater system or seawater intake should have a filtration, a heating system, because since we are working in an Arctic condition, we will be taking in very cold seawater. We must have a preheating unit to make sure that the seawater meets the optimal temperature that the engine requires to cool down. And it gave me a code which we can use to softwares like Lucid Chart, and then that Lucid Chart software can give us an entire flow chart of what steps we should take to design a system like that. And this is my seawater cooling system again, using that flowchart, just to make sure that what ChatGPT is saying does not sound so insane, or from a design perspective sounds very vivid. And it was able to deliver that just by asking from one or two, three lines of inquiries. And that would be the ending of my presentation. If you have any question, please feel free to ask. Yes, sir.
Now, when you're using the AI as a design assistant, did you find, like, when you were typing in the prompts, did it take a long time to kind of prompt it from the morning to get the right solution back?
It was right away. It was right away. As if ChatGPT was following me for the past 2 years doing my design work for my ship. And it managed to give certain details, which I, as a student, or as a human being, as a student for my marine system design program, have missed. For example, when I was a student, still I'm a student, but in second year, I was making certain design flaws, like very simple as having a filtration before my pump intake. And then I see ChatGPT not making that mistake, even though it's a student itself, but an AI student. So yeah, to answer your question, it was fast, and the response time was, it gives designers like us to waste less time on thinking, but to give us more time to imagine and find more innovative solution when all the information are right there to us. Yes, sir.
In your seawater,
So for the to understand your question again and to repeat it to my audience, in my seawater cooling systems, we are operating in Arctic condition while intaking seawater. How are we getting rid of all the ice and debris, right? So we can do one of three ways, and my instructors here can jump in if they want to. So what I learned was our seawater chest or seawater chest itself in the hull has a design that stops ice blocks from getting in. Not only that, we can use technology like air compressors to clean out the sea chest and make sure that ice doesn't block that way. We can also use hot water discharge from our seawater cooling system in that area to melt away all the ice and debris in that location. The design that Louis S. Saint Laurent uses is a reference vessel that I used for my design aspect. Is that they have a dam going all the way up, and then the water and the ice flows all the way up, and since ice floats, it keeps going farther up. Sea chest is right here. So it doesn't show you it doesn't show you the air compressor system that we can incorporate, but we can have an air compressor system here. Let's say ice blocks have blocked our way here. We can use that air compressor and blow up all the air and cleaning up our passageway there. You can also use hot water discharge and have that connection right there. I showed that in my design diagram here. If you look at it, like hot water is coming in, and then it's pushing out all my debris and ice gatherings there. The other design I was talking about that Louis Saint Laurent has is that they have a dam and a passageway here, and ice and water goes in. Ice and or snow, they float all the way to the top, and water goes in there. And sometimes they use buckets to clean off that ice that's been collected, and they throw it overboard. I hope that answers your questions. Thank you. Thank you, everyone. Oh, yes, sir.
You look at pumps. Did you look at different models of pumps? Efficient pumps, air pumps, more efficient pumps, less power, and look at what certain costs.
Thank you for the question, sir. So during my initial design phase, I did make comparisons on its power output, because cost is estimated based on the power of the motor and how much power we need to run the pump. So there were a few, like when I sent my model to DESME, they sent me one pump, but I had 2 or 3 pumps already in my mind that this might work. And one of those 3 pumps became one of the pumps that DESME selected for me. So that gives me an idea, like when 2 thinkers are thinking the same thing, that means what we're thinking kind of aligns with the design we're trying to make. So yeah, that's the only comparison I made. But after that, in my third design process, which is after the 3D model. I only made a comparison with different companies. Like I got one pump from Desmi. I compared that with another code given from Pump Plus, or what they got from the Ghouls in Halifax, I think. So that's the only comparison I made. Anyone else? Thank you.
Okay, folks, up next we have Isabella Antunes, who's going to be doing her presentation on her shuttle tanker. I'll let her give the specifics to you. This is our last presentation for the day. Enjoy.
Hi guys. You got some spoiler ready from my slides, right? So here I'm gonna talk about my shuttle tanker, the Glória Eterna, which means eternal glory in Portuguese. And so here, what I'll be talking about, a little bit about introduction and why I'm doing this ship, a little bit about economics and why it's linked to why I chose the ship, the mission profile, main operation, hull form, GA, power, electrical structure, capacities, and the final cost. So just a little bit, as you all know, I'm from Rio, Brazil, the city with the statue. And I'm a little ambitious and I like big ships. So that's the main reason why I chose such a big ship. I was always looking there at the big ships and was like, wow, that's really amazing. And that's how I came with those big guys. So in Brazil, we have a lot of oil. We are doing a lot of extraction of oil, especially southeast the basins, especially the state of Rio, my state. We have a lot of oil there, and right now we just kind of figured out the north of Brazil. Let me just use this. Right here in the north of Brazil, we just figured out a lot of more oil. So we need the shuttle tanker so we can move all this oil, right? And so a couple of things that I was asking myself when I started doing this was about the trends. Oh, people are saying that we need to be clean and we won't be able to use a lot of oil anymore. But with my research, with the demand of oil is still growing. It will still keep growing till 2030-ish. And after that, it might slow down a little bit, but still have demand of oil. And the MIT, they said we be likely to have oil for decades and even centuries. So who am I to say no to MIT, right? So the vessel will be owned by Petrobras. That's our main company for oil exploration in Brazil. And they are responsible for almost like 90% of the pre-salt exploration, which means a lot. So right now we are extracting and producing 2 million barrels per day. And so we need to get all this oil from Brazil to export and also to our country. So this client, they are responsible for 1/3 of Latin America production oil. And we are about to get one of the top 10 exporters of oil of the whole world. And they are keeping looking for more FPSOs, which are our friend vessel that we need them to do our operations. So here in Brazil, we have those 3 main routes for oil, and I'm gonna focus on China, which is our biggest consumer. They kind of buy our 39% of our oil that's set for exploration, which get us like $17 billion just for this. So they are our main client for today. So Petrobras, they were looking for this couple requirements. We need a ship that is able to do the offshore operation, needs to be built in Brazil and capable of carrying 1 million barrels of cargo. And able to go to China. So basically, I just need to be a big ship to do all this route, and also being able to stop here. It's around here, 300 kilometers from the coast of Brazil, it is where it's happening, the exploration of oil. So the ship, it will make a stop here to make this loading operation. So we need to make our client happy, right? And to begin with, I just started with the state-of-art analysis, where I checked Clarkson's website for a couple of similar ships and similar data, similar proportions for my vessel. And not only that, I also checked what type of vessels Petrobras were requesting for a couple of operations and future trends. For example, this here is the new and biggest shuttle tank China just made. It is just a little bit bigger than mine's, 280, and mine's 277 meters. And funny thing, they're going to Brazil. They built this boat just to go to Brazil to get the oil for them. So we did a lot of graphs. Don't want to put a lot of graphs here, otherwise with tons of graphs. But basically, that's how I started with this first tons of graphs. But basically, that's how I started with this first requirement of 1 million barrels. I started looking, okay, what size I will be able to carry that much of oil. So after that, I did this type of graphs and just making this analysis. So I came out with all these particulars. So the length overall of the vessel is 277 meters, with the beam of 48 and the draw of 70 meters. That's basically the ships with this size for a Suezmax size. They're basically all the ship for 277 meters. I was funny because yesterday someone asked me why not set 275, why not 280. I was like, that was a really good question, but I would say it might be with the ratio, but it was with the trend, right? So the trend, they were like 277 meters. So I'm gonna keep with this. It is useful. It is efficient. So that's what I'm keeping with. So the main operation, as I said, was to load offshore, and it's called the tandem operation. A little before, I'll have a small video of how the operation happens. So it means that the FPSO, it will change. It will have all this equipment here, and will connect to my shuttle tanker here from the bow with the BLS system, the bow loader system. So they will kind of throw the pipe hauser to us, so we'll be able to connect here and pump. They will pump to us all the oil. So we need to keep the position for that, because since we have all these connections, we need to keep a certain position. So here are the angles that are kind of safe for my operation. The green ones, the ideal one, then the yellow ones kind of need to be aware, and the red ones like, nope, you need to do something. So I know here it's in Portuguese, but I have here this distance, which is related to those angles, and some distance from the FPSO, from the vessel, from my shuttle tanker. And that's the traction for the how much traction the house pipe is handling. And here, what should the both vessels do about it? So they have all set of how to deal with everything that's going on there if something happens with the vessel, but when they need to keep with the standard. I'm not going to read all of this part. It's just a couple of requirements that Petrobras wants for a DP Class 2 vessel. So the DP Class 2, it will keep the vessel in the position. And so a lot of people think that the DP, they will need to keep the vessel in the position independently what happens, but it's kind of not it. You just kind of need to keep the position of the vessel according to the seabed of the sea. And you can control every movement. So I put here, you can control those 3 degrees of freedom: surge, sway, and yaw. And the pitch and roll and heave, you can just monitor. So you can kind of know what to expect after this. And to be sure what's going to happen, what the next steps you should be aware of. I need a lot of maneuverability to keep the position. And since the big vessel, I was like, okay, I need a lot of equipment to do that. And so I chose to have three thrusters in the bow of my vessel. In this case, here just came a picture for internet, and here on my vessel I have two tune-up thrusters and one retractable one, 360. And for the stern part, I'll also have a tonal thruster and a retractable one, as well as a CPP. So this combo will help a lot for my maneuverability and to keep my position for the biggest operation of the vessel. So with all that with all these requirements and all the needs that my vessel needs to do, I will start to do the whole form. So I just came from this thing, this cylinder, to a whole form. It took me a while. It was so fun. I remember when I was doing that, I was kind of dreaming of the lines to make like proper lines, because we gotta have a couple requirements. So as I need 1 million barrels of oil, I need a lot of space for this. So you can see here that the vessel has a really big parallel middle body. So it will be able to carry all this oil. And even though here it's a taper, but it's not the big taper, just like other type of ships, like container vessels, or even the other vessels presented here, like the Rural and stuff, because it still needs space for oil. But even though I got the taper here, so the angle of interest won't be like just a huge box, right? And I still have the bulb here. The bulb, I was kind of considering a couple stuff, because since the vessel is not meant to do in a high speed, I was considering a couple of stuff, and then doing studying stuff and studying all the notes and similar vessels as well. They all have like this type of old type bulb, and it can get me up to 5% of advantage. It's not a lot of advantage, but still advantage. And every advantage that can save you some money or the owner some money, they will do it. And I also have this taper here for the stern of the vessel, so that can have a better flow for the propellers. And so this part here is more for the accommodation parts and main engine. So, and the main part here was for the flow for the propeller. With the line span design and the pre-hole done, I can go to the general arrangement. My biggest concern here was to manage the space to be able to carry all the oil and still have space for all the equipment I needed to have there. And it was kind of fun stuff started happening when I was first started doing the general arrangement. I was kind of random selecting a couple numbers, and turns out in the end, it came the perfect frame system that I wanted. It was a really funny coincidence that happened. But I was able to carry on six in each side, 6 tanks for my oil tankers. And here I can show you the 3 thrusters here. And I have one here, the tunnel one and the retractable one for the maneuverability. So I'm gonna start talking about the general arrangement, not by the main deck, but for the main operation, the bow loading system platform. Because I was just talking about the tandem operation. So that's a tandem operation, how it actually happens when the shuttle tank gets to the offshore installation and connects to the FPSO. So they throw the first line, so they can connect the hose pipe to the BLS system. So here I have the connection for the pipe, which will get all this connection here, and all gets the pipelines going to the main deck. So just a finish of the video. So yeah, so that's how the ship gets loaded offshore. And then they take it back, and the operation's done. talking like this sounds easy, right? But it requires a lot of stuff. It especially staying on in the place. So after that, we can go to the general arrangement of the other parts of the vessel. I have those pipelines here I was talking about. So the BLS platform, they are right here. In this view, they're not showing up because I'm just showing the main deck height. So there'll be like the pipelines are coming here, so they go through all the vessel. And here I have the engine casing, some the emergency generator, and a couple other for the accommodation stuff like gym, hospital, provisions. And then we can go down to the engine room tiers. Um, I was kind of concerned in the beginning for my pump room because I still need a lot of pumps and big pumps to get all this oil out of my vessel. So when I was doing this, I was just realized that I don't have a big problem with my spacing because it's a really big vessel. And I was just, if I could have the chance to do a couple things again, I would just reallocate a couple rooms and a couple equipments there that after a couple research, I realized it could be way better managed. So here I have 4 tiers, including the tank top. And here, right here, the bow, I'm having a thruster room for all the 3 thrusters I have there. The accommodations, they are pretty standard for the type of vessel. And it was kind of fun to do this because at the beginning I was trying to do a different configuration of hallways. I was like, no, this is not working. It doesn't look like efficient. So people can just get out or, you know. My first one, I had a dead end. So when I realized what I did was, I was like, wow, I need to change this ASAP. So yeah, I have those 3. Those 2 are for accommodations. The captains and the chief engine. So this one is the captains, this one is the chief engines. They have the better cabins, right? And right here the bridge. The bridge tiers only for the navigation and some storage and the DP room, DP equipment and radar room. So now we go to the power and resistance. We start doing the whole trap and man method. And I remember when we start calculating, it was a list of a lot of variables. I was, wow, there's a lot of things. And it kind of scared me at first because I didn't know I was able to figure out everything. But it turns out in the end, well, I was able to get everything. I had a problem there because when I was doing the calculations, I was considering the half angle of entrance as it looks. So my shape here of the bow, it is really rounded. So it was almost 90 degrees of half angle entrance. So the calculations for my resistance, they were like huge. They were huge. So something's really wrong, and I will start looking for it. How can I manage this? And because my powering I was not having good powering. It's not matching with my research and from the soda and stuff. So it turns out I figured out that for the half angle entrance, it's for ships like this with this almost 9 degrees bow. You just kind of have a distance from the steam, so you can have a better angle of entrance. So in the end, I just have an angle of entrance of 56 degrees. Was way better than 90. So it was a huge impact of my design. And after doing all the calculations and already considering some losses here, I came out with this 18,032 kilowatts for my main engine, and which was a good thing because it matched with my research. Because all this type of vessels, they were all using the same engine, and it was a perfect match. When I was looking, I was like, okay, I got a good number. So I kind of have an 8% margin above, which is kind of safe to have a little bit of margin. And I'm going with a 2-stroke low speed. So for this type of vessel, big vessel like this low speed are the ideal choice. and also the two-stroke ones. They, sorry, they have such an advantage here. They are able to use the heavy oil, the HFO, which is cheaper to use, and this type of ships it requires a lot of oil, lot of fuel, and also the efficiency for this type of main engine compared to the four-stroke one for this type of vessel, it was a better efficiency. And I remember at first I wanted to try to do a twin screw arrangement, but I had a couple lack of information back there to do the twin screw. So due the time and a lot of other things we had to do for calculations, I just chose to go with the other similar vessels to use a single screw. But if I had a chance and I had a little bit more time, I would try to do the ship with the twin screw so I can have more redundancy. And also to try to improve a little bit more my efficiency. I don't think my efficiency was really good there, 53%. Me somehow I can figure out how to improve this, but at least it passed the cavitation test. I got it. And also I have the bar, the blade error ratio of 0.55 was kind of acceptable and was within the range. Everything I calculated was within the range of the vessel I was comparing to. Oh, and also we use the key chart so we can all check this how I got to all this conclusion here. The electrical system, this part for me was a little bit tricky. We use 100 loads for our research, but I had a lot of lack of data of my main electrical equipment. Just for example, my thrusters, I couldn't find a lot of information like voltage that I was supposed to have for them, and the power factor as well. So it kind of was a lack of my data. So I got a really lower expectation of power here. So it wasn't accurate what I calculated here, and we were checking three conditions. And for this ship, I considered the onboard maneuvering and on sea. The worst case scenario was, of course, the maneuvering when I was really using the five thrusters. But still, even though I was using the worst case scenario, my final result wasn't enough compared to other similar vessels. So if I have to really choose in a real state scenario, I would go with the similar that I was looking for before, which is two sets of 3,500 kilowatts and two sets of 4,500 kilowatts of MAN BMW. And which you kind of with the same brand, same model as the main engine, the 1960 20 kilowatts. So I just like to keep the same brand. So if you have something, at least you have the same brand. The match will be more accurate between them. Structure. This part was fun and tricky. So we use Lloyd's, and as you know, English is not my first language, and I struggle a lot of Lloyd's to do the structure. So I spent a lot of time asking Wilson about it. I'm like, I can understand this, what's going on, and to be able to understand all the calculations. But and in the end, I was able to manage to do everything to have my Scanley book done, and I really enjoy doing this part of 3D modeling. I'm the type of person that really enjoys see what I'm doing, and having the 3D model helped me so much realize what was going on my vessel and if it was kind of accurate, if it makes sense or not. So I'll be using mild steel for my vessel. As I said, going for Lloyd's regulations, and for the parallel middle body, which is the biggest part of my ship, I'll be using the longitudinal framing system. So we will, so I can have some weight efficiency, so kind of reduction of my weight, and also for my longitudinal bending. So I'll keep with this system for the majority of the vessel. But when we get to the ends of the vessel, I'm gonna switch for the transverse framing, but not the whole vessel. The main deck will keep on the longitudinal frame system, do it for structural continuity. So those are my fore end and aft end. Here, I changed the frame system and also this frame spacing. So for the parallel with the body, and then just go back here for a bit. I was using for this part here 4.8 meters of spacing, because here was not a lot of things kind of going on, was just more structure for my oil. There's nothing going on here basically, so I just need to keep my longitudinal bending okay with all these calculations and section modulus and stuff. So here I was able to manage to have this a little bit more spacing. And the longitudinal frame of the girders it's 7.2 meters apart, and the longitudinals they are 800 millimeters apart of each other. When I get to the ends here, I switched, right, as I said, to the frame, the transverse framing, and the spacing here changed to 3.2, because here though this space we need to be more ready for more impacts from the sea. So this closer structure will kind of help this to handle this part. And also here we have way more shapes than this part here. That's also why I switched for the transverse frame system here. So I have the flats, the engine flats. They are keeping with the track with the structural continuity. I kept with the same height as my stringers from the whole vessel. And here, as I said, the 3.2 meters apart of my beams, my deep beams. So, and also this part here is also more structured because it kind of need to handle all the vibration and all forces that came from the propeller. So the tank capacities, my biggest concern first was to have enough space to carry 1 million barrels of oil. So when I was doing this, I was kind of concerned. When you see just this part here, I was like, okay, it's just like a lot of squares. I think it'll be fine. But after when you keep doing the stuff, you just realize that, oh yeah, just get a taper to the water line, right? So when I was getting here, I was started to get a little bit worried about it. But so I was managing to keep a good position of my bulkhead so I can have enough space. And it turns out in the end, I have a little bit extra of oil. I can carry a little bit more than I'm supposed to carry. So I'm within the range. And also my other concern was the ballast system. For the ballast system, I'm going to talk a little bit more when we get to the trim stability part. I'll be using one of the tanks as a ballast system. Because one of the vessels that was inspiring to do my GA, the way he did the arrangements, it was to use one of the tanks as a ballast tank. So when I get to the ballast, I will have all this part here. I have the aft peak tank here and all those ones, and the fore peak one, plus those two. They are the cargo tanks number 4. I'm gonna have to use them as a ballast as well. I'll be for the full capacity. I got 4,826, and was a little bit more than I was planning, which is good because I want to have a little bit of a margin of what I actually needed, considering everything I need to use. And I found a different thing about this vessel that I won't have the black water tank because I'll be having the marine sanitation device. And since it's not a lot of people, I'm only carrying 25 krill. The marine sanitation device will be able to handle without having the black water tank. Just put this slide so we can have a better viewing what's going on with my tanks. So the yellow part, they are for oil. These light blues are for ballast. Slop tank here, the purple, and this one's the HFO. So it's kind of what's going on here for the tiers. I separated them for the really close. The HFO tanks are really close to the other one, the first one, the bigger one, and I try to keep them on the wings. But there's a separation here for the cofferdam, so I don't have the. They are not really close to the. They're not close to the water, right? So the trim stability, we follow the IMO standards for the trim stability, and we run 9 conditions for departure, mid-voyage, and for arrival. Each condition it was tested for when the ship has only ballast and only cargo and partial, like 50-50 of them. Considering like for departure, with all my consumables on full, the mid voyage they are like half, and the port arrival they're around 10% of consumable left. So here it was like the most kind of stable scenario was when I'm full loaded with my cargo. I got to almost 170,000 of displacement in this part here, and it was passing. It was really good. I was really pleased when I saw that everything was going on. When I saw all of this speed here, and here was when my worst case scenario was when it was just ballast water here. It passed when I first did it, but the problem that I had was the trim. I had a really big trim here, like not a trim, but my waterline here was really above. So my half of my propeller was outside of the water. So I kind of need to fix this part. And I could have started doing this by ballasting one of those tanks here, maybe this lock tank or the number 6 cargo tank. But the problem is when I was doing this part, the vessel was trimmed, was really trimmed, so wasn't like sea keeping. Was not able to make a good navigation of this. So when I was looking for and reading a little bit more, the one of similar vessels it was using the cargo tank number 4 as a ballast system. So when I tried to do this, when I switched using the cargo number 4 as one of the ballast tanks, I kind of have this steady position. So now my propeller is deep enough, and I still pass and with a reasonable trim. So for the cost, using the carry-out method, I got for this $173 million. It's a little bit above what I was expecting, but when I was looking at considering the average cost of 150 million, I was thinking about the carrot method. It was considering a higher pay for the workers. I know sometimes it's kind of hard to say something like this, but in other countries, the hour for the pay they were really lower. So when you consider this lower pay rate, you can get you'll be able to get a more reasonable average cost. So I also, since the vessel will be built in Brazil, I was considering also how it would cost if it was built in Brazil. So I would have around 140 million if it was constructed in Brazil, and if it was constructed in China or South Korea, it will lower. It would be around 110 million to make this vessel, because I was looking on the average of the workers in these type of countries. So basically, constructing the ship is way more worth it to make it in other countries that outside of America or Europe, which they have the higher pay rate. And when I was doing this, the steel part was the most expensive part of my vessel because it requires a lot of steel to make all this big vessel, right? And the steel workers, they were also around my biggest cost. Each of them, the price of steel and steel work, they were around 20 million each. So when it changed the main things, you just can have a cost that's average and you still can have a good profit of it. and closing comments about everything that I did. I wish I could do a couple things again. For example, reallocate a couple control rooms, and especially my engine room part. I wish I could relocate a couple stuff. As I said before, revisit my powering aspects. I would love to try and see what would happen if I had to choose a twin screw system. If it would be better or not, more efficient or not. Take a look for closer, like smaller details that I might have missed. I, of course, missed a couple details. And the thing that I think I would love to get back again was for the scaling calculations. Even though I struggle, as I told you guys before, there were a lot of calculations that we were not able to perform because they were set as direct calculations. So I was not able to perform to have more accurate numbers for this. So a couple parts of my vessel, it is kind of overbuilt of my calculations. And it's strong enough. It's strong enough. But I wish I could revisit so I can have a more accurate numbers for my structure. Oh, and just a thing that I forgot to mention about for my trim stability, I just kind of remember here. I remember I was not passing my floatable length. Well, I thought everything was fine, but then in the end, I was like, my God, what's going on? And I figured out I made a major mistake with my bulkhead. This bulkhead here, I just realized I just used this bulkhead here up to the main deck. But when I realized that I made this mistake of this bulkhead here, that other vessels, they had this bulkhead up to the forecastle deck, it was passing like really good. So it's floating and it's safe now. And yeah, so if you guys have any questions. Oh, sorry. It was the version with the sound. So this vessel aids equipped with a scrubber, so and reduce emission of the animal pets. So we use the scrubber, so it will be less harm to the environment.
I have a question from the live stream. So the person did say that they missed the beginning, but they came in when you were talking about refueling. So they just want to know, why do you refuel at sea from the stern and not the side?
So I'm not refueling from sea. My vessel will leave full from Brazil, and it is ready to go up to China with the full capacity. What I'm doing offshore is to get the oil from the FPSO. That's what's happening. I had another question here coming. No. Yeah.
Similar to me, comes to Dallas box.
So I was using there was a couple of equipments that I was looking for, but I need to confess that I was like really into the type of equipment. But he has space for this type of equipment actually I assigned one of the spaces for the fire part and for some machinery. At my machinery arrangement, I put some equipment there, but I can't tell you right now which type of equipment I would be using. But I can check and get it back to you. Yeah, I mean, in space, I have a lot of space there, so I can manage to do this. It's a CPP. Yeah, because the CPP will better for the maneuverability of the vessel and for the DP2 requirements. Yeah, sure.
You know, from the research, they China, they contact the same
Yeah, they usually do the same route. The fastest to go. Sorry? Oh. Yeah, it's usually the same route. I was looking at it again. It was usually the route they go, they're coming back.
No.
It's fun. Well, thank you guys. Thank you for coming. I just want to thank my family. My family and friends. They're all watching from Brazil. So thank you guys. Beijo, amo vocês. Thank you.
Thank you, Isabel. Well, folks, that concludes our presentation today. I hope you all enjoyed. If you got any other questions, we'll be around. We'll be in the classroom afterwards. Thanks so much. Switch this to